Hello, everybody. So we are going to start off with simplification chapter. Okay, and in any of the exams of SSC or any competitive exams, you would find around two simplification questions for sure. And two questions mean a lot because out of 25, if two questions are coming, then it is equal to around 8% of the total weightage of the entire examination. Okay, so you need to focus a lot on this, and it's going to be very, very important. Okay, so the main point in simplification is that you'd be given a simple or maybe a complex area, a complex equation you'll be given, and you'd be asked to simplify the equation to create your to create an answer out of it. Okay, you'd be asked to simplify the equation to create an answer out of it. So the most standard form and the most basic form that we follow for simplification, and the most fundamental thing which I am going to teach you is BODMAS. Okay, is called BODMAS. So what happens in BODMAS is that you have to follow a certain preference pattern. Okay, you have to follow a certain preference pattern in which you are supposed to solve the equation. If you don't follow that, you are definitely going to mess it up. So trust me, this is the most fundamental and the most important thing that you must follow each and every time. I'll tell you what BODMAS stands for. It's basically an acronym, and BODMAS stands for B as in brackets, B as in brackets, then O as in order or off. Okay, order and off. I'm going to tell you what order means and what off means. Then D, D stands for division. M, M stands for multiplication. A stands for addition, and S stands for subtraction. All right. So this is the order in which they work. Uh, Further, brackets also have their internal order. Okay, they have an internal order of their own. And what does the internal order say? The internal order says that you have to follow the bar first. Okay, anything with the bar on top is supposed to be given the first preference. The second preference is supposed to be given to round braces. Okay, is supposed to be given to round braces. Then the next preference is supposed to be given to curly braces. Okay, these are called curly braces. You can call them brackets, you can call them braces, it's almost the same. And then last preference is given to square braces. Okay, these are called square braces. So that's where our entire preference system of the bracket lies. Then in terms of order and off, so order means anything with a sign of exponent on it. Okay, exponent or roots on it. Okay, exponent or roots on it. And off simply stands for multiplication. As I've already told you that this is the order which you'll have to follow. If you encounter off in an equation and you encounter multiplication in an equation, then you're supposed to solve the off equation first and then move to the multiplication equation. Okay, so this is how we solve the order situation. And then comes the division situation. A division situation is nothing but the reciprocal of multiplication. Okay, a simple division equation, I need not teach you much about it. Then a multiplication equation is very simple. Also, the division or this entire equation is going to work from left to right. So it is essential for you to solve the equation from the left hand side to the right hand side. Then talking about addition, addition is simple addition. Talking about subtraction, subtraction is simple subtraction. A bigger number from a smaller number would give a positive output, and a smaller number from a bigger number would be a negative output. Or I am wrong. If I subtract, if I subtract a bigger number from a smaller number, okay, so there is a minus sign over here and there is a smaller number over here, my output is going to be negative in nature. And if I go for a negative, or if I go for a big number and I take out a small portion out of it, my result is going to be positive. Okay, so all this was a part of the basics that we teach. Okay, now I'll be jumping straight onto the questions. We have 1, 2 and 3, 4. We have 4 questions before we finish off the first concept. The first concept is of BODMAS. Now I'll be solving this question. Okay, so here you see that I've already spoken about BODMAS. Okay, I've already talked about BODMAS. So we'd be solving the brackets. We already have the bracket, and the first priority is supposed to be given to the bar bracket. Okay, so what I'll do is I'll immediately solve it. So 7 minus 3 is nothing but 4. So we have 4 over here minus, this is 14, and it is already inside the curly braces, the round braces. So we have solved it. Okay, we have solved it. Now this curly braces would come here, these curly braces would come in here. Okay, I'm pretty bad at drawing the right hand side curly braces, so the left hand side ones would be definitely very good. So the minus sign over here, the off symbol over here, the 5 over here, the 15 over here, and the 22 over here. Okay, you need not write the entire equation straight away. Okay, you can pick up points from somewhere and solve them and then move on. Now the brackets, these curly brackets have their priority. 14 minus 4 is 10. This curly braces would be gone and minus would come here, off 5 would come here, 15 would come here, another minus, and another 22 would come here. So I can solve this off now. 10 of 5 is equal to 10 into 5, which is also equal to 50. Okay, so this is 50. 15, there is a minus sign, there is a 15 over here, and there is a 22 over here, another minus sign. Okay, so 22 minus 15 minus 50. So 22 minus 15 is going to be a plus 7, and minus 50 and a plus 7 would make 43 negative. So minus 43 is my answer. I'll take you through it one more time. There is a bar which I need to solve at first, and there are also curly braces, there are also round braces which I need to solve first. So I solve this out. 7 minus 3 is equal to 4. Then I move on to the point. Then I move on to the point where these curly braces need to be solved. So these two curly braces are solved in this manner. 14 minus 4, okay, which gives me 10. Then 10 is multiplied by 5 because of the reason that there is off in them, and then there is a simple negative sign. Okay, a simple negative sign between all the three. So whichever way you want to do it, it's unidirectional, it's omnidirectional. Okay, you can start it from left hand side or right hand side, not omni but bidirectional in this way. Okay, moving on to the next question. This might seem a little hard to you. Okay, it's not very hard. So I have this entire equation. I can move from left to right, and the highest preference is given to round brackets over here because there is no bar over here. So I will solve this first, and inside these brackets there is another preference order which I need to follow. So it would be 14 multiplied by 7 divided by 14. Okay, so this is what I need to follow over here. Minus, similarly over here there is another preference order which needs to be followed. 12 of half needs to be followed first, and then a division needs to take place between 18 and 12 into half. Okay, 12 into half minus 2, there is a division sign, 8 plus 25. So this is actually in round braces. Okay, this is actually in round braces. I'll quickly erase it. This is actually in round braces, and the other thing on the outside is in square brackets. Okay, square brackets. So I'll solve this one more time. I'll take one step ahead. 14 would get cancelled. by 14, and this would give me a result of 7, minus 18 divided by 20. This thing, this 12 into half would take precedence over the division because there was an off involved in it. Okay, there was an off involved in it. So in whenever we do BODMAS, this off takes precedence over D. Okay, so off is solved first. 12 into half is 6. 18 upon 6, or 18 divided by 6, this would give me an answer as 3. Now I quickly come here and solve this. 8 divided by 2 would give me answer as 4. This would be plus, and I would have 25. Now everything is left in the terms of plus and minus, so I can quickly solve them. 25 plus 4 is 29. 29 minus 10 is 19. Okay, 7 and 3 make 10 and minus sign. So 19 is an output of it, and that is my final answer. Okay, moving on to the next question. Now it has a little bit of calculations involved, so I'll quickly do that. 26, first I'll go to the bracket, the smallest bracket which I have, the smallest, or I should say the most preferred bracket, which is the round bracket. Okay, so in the round bracket, I would see that 26, there are two operations that need to be done: minus and multiplication. Multiplication has a higher value versus minus, so I'll multiply first. Now what I have to do is 26 multiplied by 112. What I'll do is, I am forgetting all the decimals in the question. I'll make them reappear later. Okay, so 112, I can split it into two parts: 110 and simply 2. Okay, 110 and 2. This decimal need not be here. This decimal need not be here. So 110 when multiplied by 26 simply turns out to be 2860. Okay, and when 26 is multiplied by 2, it simply gives me 52. So I'll add both of them up. And this would give me 2912 as my output. So 2912 with 3 decimal places. As we are multiplying the two numbers, the two decimals of this point and the one decimal of this point would add up to give me 3 decimals. Okay, or I would rather say that 26 divided by 10 multiplied by 112 divided by 100. Now these two get along to make 1000, and the 1000 represents a decimal. Okay, so 2912 is the output of this small portion. I'll preemptively solve it for 2.1 minus as well. Okay, I'll just show it to you what I have done. 2.1 minus 2.912 was my next step. There is an off over here, and there is a 0.6 multiplication plus 2. The curly braces start over here. Okay, I should solve them like these are the curly braces, minus 5.6 is my output over here. So I would preemptively, like preemptively means to go one step ahead and solve this. This output would become negative because 2.9 is greater than 2.1. So the output here is 0.812 minus 0.812 minus 0.812 would be multiplied by 0.6. Okay, this is 0.6. I'll just clean it up. Multiplied by 0.6 plus 2. This entire story is in curly braces, minus 5.6 is over here. Okay, I'll quickly do this. 6 2s are 12, 6 1s are 6 7, 6 8s are 48, and there would be 4 decimals over here. Okay, there would be 4 decimals, so this all would be absorbed inside, and the minus sign would again come outside. So 2 minus 0.4872. Okay, and there is also another minus over here, and 5.6 is also here. So I'd be taking this on the right hand side now. So 5.6 minus 2 is equal to 3.6. This minus would turn into a plus, and 0.4872 would come out as my output. So I just need to add them up now. I just need to add them up now. So there would be 2, there would be 7, there would be 8, there would be 0, and there would be 1. Okay. So 4.0872 is my final output. I hope you understood it. Okay. The main factor was the main catch point. The main catch point was nothing but calculations with decimals in it. Okay. Calculations with decimals in it. So if you're clear about how to put the decimal and where to put the decimal, that's how you'll be able to ace through the exam when such questions come up. Okay. Now coming to the last question of concept 1. This question has a couple of multiplication signs and division signs and whatnot. Okay. So what we'll do is we will try to find out the delimiters. Okay. We'll try to find out the delimiters. We are pretty sure about one thing. Then whenever we are solving with BODMAS, division and multiplication has the same preference level. Okay. But still, when we're moving from left to right, the division occurs first and the multiplication occurs later. But the addition and subtraction, they can be set aside. Okay. Because division and multiplication gives a very huge change in the result. But a simple plus and a simple minus doesn't really change the equation that much. So what we'll do is every time we encounter a plus or a minus, we will let it be. And every time we encounter a multiplication or a division sign, we will solve it right away. Okay, we will solve it right away. So what I'm going to do over here is I'm going to rub it off so as to help you what and where I'm coming from. Just give me a moment. Okay. Yeah. So 11 multiplied by 11 is 121. The square of 11 is 121. I'll use the simple plus sign. 11 divided by 11 is 1. Minus 11 into 11 is again 121. There is a plus sign. There is another 11 over here. And 11 multiplied by 11 is equal to again 121. Minus, there is a simple 11 kept over here. Then again another minus and 121 is there in the end. So I have 121 and minus is gone. The other one is also gone. Okay. There is a plus 11 and there is a minus 11 and there is only one plus 1 left. Okay. There's only 1 plus 1 left and that is my correct answer. Okay. I'll repeat what I said. Here I can see multiple multiple division and multiplication signs together. But there is a delimiter. There is a delimiter means there is a limiting option. There is an option which limits things. Okay. So these pluses and minuses can be dealt with later if we deal with the multiplication and divisions first. Okay. So these are my focus points. Okay. Wherever I find a plus, everything that is around it, let me simplify it. So I don't have to break my head. Okay. So I don't have to break my head over it, that whatever I'm doing, it's supposed to be very, very correct. So this and these questions, trust me on this, 30% people 30% people easily get these questions wrong. So I would recommend that kindly focus a lot when we are doing this. We'll be moving on to the next concept. All right, so we are on the second concept, and the second concept of simplification constitutes fractions. Okay, fractions. And see, we are already learning about the most fundamental concepts uh, of the entire examination, which are simplification. But we are delving deeper into the concept of simplification, and that portion also contains a subtopic that is called fraction. Okay, or fractions. So what happens in fraction is that the most standard form of seeing a fraction, whenever you encounter a number, so you can say that it is a part of a fraction when you can you can represent it with a dividing line. A dividing line. Why do I call it a dividing line? Because in reality, this is an operation. This is an operation which is being conducted. The operation is that of division. Okay. There is a dividing line and something is written on the top, let's say X, and something is written on the bottom, let's say Y. Okay. So in this portion, what we can see is that y has been divided into x parts. Okay, y has been divided into x parts, or there is a portion of x or of y which is represented by x. Okay, there is a portion of y which is represented by x. Let's assume I say 1 upon 2. So if 2 is an independent quantity, and when I say independent quantity means it is not dependent on something else for its own existence. If 2 is an independent quantity, then 1 represents a portion of 2. And how much of 2? When you divide 2 into the smallest parts possible, smallest real parts possible, smallest real as well as integers, so it would break down into two portions. Okay, 2 would split itself into two portions, that is 1 and 1. So if I pick 1 out of it, so it's basically representing half. Okay, so 1 by 2 as a fraction represents half. Now there are, see, this might seem very, very complicated, but for the ones who are not able to understand this, I would request you to rewatch the video. If you still don't understand it, it is a little complex. Okay, when you see it, when you solve it, it's very easy. But just as the basic understanding, it might be a little difficult. But no problem, hang on with me. We'll be diving into better portions of it, okay, where you'll understand things like very easily. So there are like around 4 5 types of fractions. Okay, the first one being a proper fraction. Okay, there is a proper fraction. So what happens when I talk about a proper fraction? In a proper fraction, the numerator is lesser than the denominator. Okay, for example, 2 by 3, 3 by 7, 4 by 9, 8 by 15. So in all these fractions, what you can see being common is that the numerator is lesser than the denominator. How does it help you and how does it define it to be a proper fraction? Is that whenever the denominator is bigger, so we can see that something that is in the denominator is being split apart, and something that is there in the numerator is representing it. So the pieces that have been broken down, if they are equal to or less than the one sitting in the numerator, that is when we can simply declare it as a proper fraction. See, it's important to understand these terms because SSC these days is asking like very, what should I say, very fundamental questions, which most of the people get wrong. So, in a proper fraction, the numerator is always going to be less than the denominator. Then, if there is a proper fraction, then there is an improper fraction as well. There is an improper fraction as well, where the numerator is greater than the denominator. Okay, so in this example, 5 upon 2, 3 upon 1, 4 upon 3, 7 upon 2. Okay, so in all these numbers that I have represented, in all these fractions that I have represented, the numerator is more than the denominator. This means that the denominator, when it is split into its most basic parts, the numerator is much more than the denominator's split parts. Okay, so it doesn't represent a proper fraction and it is an improper fraction. And whenever I say fraction, a fraction is basically a piece of something. If there is a bigger thing, then only you can expect a piece of something. Got it? Fraction means if there is a bigger piece of something and I pick out a few pieces out of it. If there is, let's assume that there is a big cake over there. Okay, a big chocolate truffle cake, and if you cut it down and you eat, let's say this big a portion, like there were 8 pieces in which the cake was cut, and I pick out one piece and eat it, so I ate 1/8 of the cake. If I eat 2 pieces, then I ate 2 by 8 or 1 by 4 of the entire cake. So that is a that is a proper fraction. Improper fraction is when I say that I ate 9 by 8th of the cake. Let's assume that I did 8 pieces of the cake and I ate 9 by 8 of the cake. So this is an improper fraction. This means that there was definitely one entire cake plus one extra piece of cake. Okay, one extra piece of cake was there. So this is what creates an improper fraction. Coming down to part 3. Part 3 is mixed fraction. Mixed fraction. So what happens in a mixed fraction is that whenever we encounter that the numerator is bigger than the denominator, we can represent it in this fashion: a b by c, where if you wish to create it to the where if you wish to create it from a mixed fraction to a proper fraction or maybe an improper fraction, then the answer would be c multiplied by a plus b whole upon c. Okay, and we've already seen that this entire equation, which is sitting in the numerator, would be solved in this format, that c would be multiplied by a first and then b would be added into it, whole upon c. Okay, I hope you get this mixed fraction concept pretty well. Moving on to the next point, then there are equivalent fractions. Equivalent fractions. I know most of you might be knowing everything that I'm talking about, but trust me, in the examination, there comes a time when you have to read a definition and you simply can't recall. So it's better that you pay a little attention over here and get the right definitions across your mind. Okay. So equivalent fraction. When I say, see, this is not equivalent fraction, it is equivalent fractions. So this means we are talking about two or more fractions. When I say that two fractions are equal, that means there would be equal numerators and equal denominators in their simplest form. In their simplest form. I'll tell you how. Let's assume I write the number 3 upon 9 and I write the number 4 upon 12. Okay? If you see it like at first sight, at the first instance, you would say that these fractions are not equivalent. Why? Because 3 doesn't match 4 and 9 doesn't match 12. Okay, the 3 doesn't match 4, the numerators are different, the denominators are different. At the first hand experience, you would say that no, these fractions are not equivalent fractions. But if you break them down to the simplest form, and how do we break down the fractions to the simplest form? The simplest way of doing that is to divide the fractions, both the numerator and the denominator, with the GCD, the greatest common divisor, or in other words, there should be an HCF, the highest common factor. In this case, there is 3, 3 ones are 3, and 3 threes are 9, and there is 4 ones are 4, 4 ones are 4, and 4 threes are 12. Now, I can easily say that 1 by 3 is equal to 1 by 3. So, the first assumption which I started off by looking at it directly and saying that 3 by 9 is not equal to 4 by 12 means I was wrong. These fractions were not in their most simplified forms. The GCD was not removed from it, the HCF was not removed from it, and it was a higher form. So you have to bring it down to the simplest form first and then equate them and then check if they're equal or not. So when this sort of when you encounter two such fractions which are equal, once they have been brought down to this simplest format, that's when you can declare them to be equivalent fractions. Okay. One last point, there is something called continuous fractions. Okay. There is continuous fractions. So what happens in continuous fractions is this, that let's assume there is a number which is equal to x, and this is now moving itself to this format: a0 1 upon a1 plus 1 whole upon a2 plus plus 1 whole upon a3, and so on. So Whenever you encounter such continuous fractions, that is when you simply identify them as continuous fractions. Whenever we'll be encountering such questions, I'm pretty sure in the next few slides we will find this question. We are supposed to do nothing. We are just supposed to follow this simple format of mixed fractions. Okay, we'll be picking up this simple format of mixed fractions and we would be applying it. Okay, so if we need to solve this, we have to go up the ladder. A3 multiplied by A2, so this is equal to A3 into A2 plus 1. This entire thing comes in the numerator. One comes in the numerator and entire thing goes in the denominator, and A3, which was here in the denominator, moves up and goes to the numerator. Okay, so this is A1. So this is how we will move up the ladder. It might not be visible and might not be very clear to you right now, but once we have an example, then you'll know it very well and you'll know it much better. Okay, so this is a question which we are supposed to solve, but I would like to introduce a very simple, I'm sorry, a very simple and a very small understanding that I want you guys to have. Let's assume there are two fractions, a by b and c by d. These fractions like a, b, c and d, these being variables, can have any value in them. Okay, they can house any value in them. So a by b and c by d are two fractions. Okay, a by b and c by d. There are four operations. There are four standard operations which you can apply on them. One is plus, the second one is minus. These two are like clubbed together, and the third operation is multiplication, and the fourth operation is division. Whenever you are supposed to have a plus operation between a by b and c by d, at that moment you need to have the denominators to be common. Okay, you need to have a single denominator. When I say denominator, everything that is under the bridge. Okay, this bridge that you have, the water under the bridge, okay, that's an idiom. Water under the bridge means let bygones be bygones. That is another idiom. An idiom within an idiom, so that's Inception, the movie. So water under the bridge means let it go, whatever has happened, and the past is the past. And let bygones be bygones also means that like whatever has happened in the past, so let's chuck it. Okay, chuck it is another idiom, not an idiom but a phrase. Chuck it means just bite it and like forget it. Okay, so a by b plus c by d are is the operation is plus, and these are two different fractions. So once there is a by b and then there is c by d, if you wish to add them, you need to have a common denominator, that is b multiplied by d. When you'll have the common denominator, you have to take basically the LCM. I'm not taking the LCM over here. I'm simply multiplying a and b into d, then a into d plus c into b. This is how it is going to come up with. Okay, simple. Whenever there is a plus sign, you have to do this. Whenever there is a minus sign as well, you need to have the denominators to be common. Okay, ad, this is ad minus cb whole upon b multiplied by d. So we are pretty clear on this. Whenever there is a plus or a minus, you have to have common denominators, and to do that you will have to multiply the same thing or the LCM of the denominators with the terms both numerator and denominator. Then coming to multiplication, in multiplication, a by b when multiplied by c by d, this is a very simple operation. The final output which you will have is ac upon bd. Okay, do not shy away from these things. These are very fundamental and very important things. A upon b when divided by c upon d. Okay, so what happens with this is some people might feel that we have to create a reciprocal. Okay, some people might feel that we have to create a reciprocal. It's true that you have to create a reciprocal, but only on one of the fractions. Okay, and one of the fractions should be the fraction on the right hand side. Okay, you can have like you can have the numerator, the reciprocal on the first fraction as well, but in the end you'll have to flip it one more time. You will have to do the reciprocal one more time. So the best way to solve it is a by b multiplied by d by c. Okay, what I mean by reciprocal is reciprocal reciprocal is reciprocal of c by d is equal to d upon c. Okay, reciprocal. You flip it. Simple. A by b into d by c. So the final output comes out to be ad upon bc. Okay, so you have to flip one only one fraction. Okay, this is fraction 1, this is fraction 2. In multiplication there is no flipping required. Simple numerator multiplied by numerator and denominator multiplied by denominator. So what we're going to do is we're now going to solve this question over here. This is the concept side which I taught you. Now talking about this, let me solve the mixed fractions first, because this is going to be like, this is the only thing which is going to come in the way of me like solving the question very well. 1.5, when you solve it in mixed fraction, I'll solve just one of them. I'll just solve one of the mixed fractions, and rest of them I'll do them a little verbally. Okay, 2 ones are 2 and 2 plus 1 is 3. So 3 upon 2, or I'll just do it one more time. 2 multiplied by 1 plus 1 whole upon 2 is 3 upon 2. Simple. So coming down to this, 3 upon 2 plus 10 upon 7 divided by, I've done 10 upon 7. Okay, 7 ones are 7 plus 3 is 10. And then I'm going to use the round bracket. 5 ones are 5. 5 ones are 5 plus 3 is 8. 8 upon 5. Off means multiplication. And 4 ones are 4 plus 1 is 5. 5 upon 4 multiplied by 3 twos are 6. 6 plus 1 is 7. 7 upon 3 whole divided by 3 twos are 6. 6 plus 2 8. 8 upon 3 divided by 4 by 9 multiplied by 5 by 6 plus 14. Okay, now I'll be following my favorite. Okay, my favorite and maybe your favorite as well, the BODMAS rule. I see the brackets over here. I'll solve them quickly. 5 ones are 5, 5 ones are 5 gone, 4 ones are 1, 4 twos are 8. So the output of this entire bracket is equal to 2. Similarly over here, I see there is a division sign. The division sign means I can flip it. Okay, 8 by 3 multiplied by 9 by 4. Then again another multiplication of 5 by 6. I'll solve all three of them together. Okay, 4 twos are 8, 3 threes are 9, and 3 twos are 6, and 6 is gone. So the output of the denominator, like this portion of the denominator, is nothing but 5. So in the denominator I can write 5 plus 14, that is 19. 5 plus 14, that is 19. And then in the numerator what I would get is, there is a division sign over here. Okay, so 3 by 2 plus 10 upon 7 multiplied by 1 by 2 multiplied by 7 by 3. Okay, as you can see, I've removed the division sign and made it a multiplication sign, and I've flipped it. Okay, I have flipped it. I'll just rewrite this point. This is 10. Okay, so this is 2 5s are, this is 7 7s are. Then what we have over here is 3 upon 2 plus 5 upon 3 whole divided by 19. This gives me 6 in the denominator and 19 in the numerator. So 19 upon 6 multiplied by 1 upon 19. This 19, I've written it as like it was in division. So this division can be carried forward to into 1 upon 19. We are going to still be dividing the same numbers. So 19 would be cancelled with 19, and my final answer would come out to be 1 by 6. Okay, I hope that's easy. That's good. Let's move on. I need to evaluate this entire expression, and I would want you to be with me. Okay, just be with me. We'll solve it very quickly. We'll be using the BODMAS technique, but I should first of all get rid of this bracket. This might sound to be like look like a bone of contention. Then there is an off over here. So all these mixed fractions, they should be taken away ASAP. So I'll be focusing on the right hand side first, then I would come to the off side, and then I would ultimately multiply both the fractions separately. So the first thing that we look over here for are the mixed fractions. Okay,
these mixed fractions are the only problems which we're gonna have, because if you cannot just simply go and, let's say, subtract 3 from a half. Okay, you can do it, but let's not complicate matters to that level. Let's keep it simple. Okay, 3 3s are 9, plus 1 is 10. So it is nothing but 10 by 3 minus 2 and a half means 5 by 2. This whole comes in a curly braces. Okay, let's assume this to be a round braces. Okay, there is a division sign, there is a half, and there is an off sign over here. Then 4 ones are 4. This comes out to be 5 by 4 whole divided by 1 by 3 plus 1 by 5 of 1 by 9. Okay, and there is an off symbol over here as well. Then there is 0.04 upon 0.05. Okay, when we remove the decimals from here, what we get is 4 upon 5 directly. Okay, I'm going to put 4 upon 5 directly, because the decimals are going to are like going to cancel each other out. If we remove the decimal, we're going to get 100 in the numerator and 100 in the denominator, which ultimately cancels itself. Okay, so in at this point, we are able to see that in the numerator there is an off sign. Okay, the off sign has a higher precedence as compared to the divide sign. The off sign has a higher precedence as compared to the division sign. So we are going to solve this first. So half multiplied by 5 by 4 is equal to 5 by 8. Also, I'll just remove this 5 by 8. I hope you can recall 5 by 8 being the output. There is a division sign over here. Okay, so the division sign, then 5 by 8. Now 10 by 3 minus 5 by 2, I'm going to cross multiply. 2 tens are 20, 3 fives are 15, 20 minus 15 is 5. 5 upon 6, there is an off symbol over here, whole divided, and 1 by 3 plus 1 by 5 nines are 45. Okay, so we've reached this point where there is 4 upon 5 of the numerator and the denominator. Let's solve the numerator first. 5 by 9, I'm going to solve it right here. 5 by 6 multiplied by 5 by 8. In division of fractions, one of them has to be reversed. One of them has to be reciprocal. Okay, so this gone, 2 4s are 8, 2 3s are 6. This is 4 by 3 is a numerator, and simply 1 by 3 plus 1 by 45. I need to have the numerators to be the same. So to make the numerator of 1 by 3 to make the denominator same, I need to have 45 in the denominator of 1 by 3. So I'm going to multiply the numerator as well as denominator, the numerator as well as a denominator by 15. So this is nothing but 15 by 45 plus 1 upon 45. So I have 4 by 3 in the numerator, as in this case, and I have an entire denominator which is equal to 16 by 45. This off stays intact, and 4 by 5 comes here from the top. Moving ahead, 4 by 5 multiplied by 4 by 3 multiplied by 16 upon 45. The one in the denominator, inside the denominator, if there is a numerator, that will shift itself to the denominator, and if there is a denominator, it will shift itself to the numerator. This is the flipping rule. Okay, this is the flipping rule. Now 4 4s are 16. This is gone. 3 5s are 15. 15 3s are 45. The final answer is 3. Okay, we'll be moving to concept number 3 now. So we are now at the third concept, and the third concept is a very interesting concept. Why? Because you can find almost one question in every examination of this sort, and this is apart from the two questions which I talked about in the first concept. In the first concept, I declared it very, like, with a very firm tone and with a lot of credibility, that two questions come from simplification. But this is the third question which comes from simplification. And this question is nothing but comparing the fractions. Okay. This question is nothing but comparing fractions. What happens when we compare fractions? Let's assume that there are three fractions a by b, c by d, and x upon y. Okay, these are three fractions. What comparisons can we draw from the entire equation? So this is not an equation because there's no equal sign, but what comparison can we draw between three independent fractions? A by b is not equal to c by d is not equal to x by y. So this is not an equation. These are just independent variables or independent fractions. So let's assume that a by b is greater than c by d and c by d is greater than x by y. So how can I draw this conclusion that the first one is the biggest of the three, or the third one is the smallest of the three, and why is the second one lying somewhere in the middle of the first one and the third one? So for this, there is a very standard, there are like three steps that you need to follow. Number one, have common denominators, right? If somebody comes to me and tells me that there were three cakes at the party, let's assume cake number one, cake number two, and cake number three. The first cake and the second cake and the third cake. And the three cakes weren't equal. They weren't equal. If somebody brings me this bigger size of the first cake, and somebody brings me this bigger size of the second cake, and somebody brings me this bigger size of the third cake, these three cakes are not comparable. They cannot be compared. Why? Because we don't have a weighing scale, and we can't really say unless we know what their father was like. When I say father or what their mother was like, what I mean to say is the piece or the portion which has come out of of a bigger fraction cannot be compared unless the parents are equal. Had the three cakes been equal, the first one, the second one, and the third one, then we could have easily said that the three portions which have come out of it, or the three pieces which have come out of it, just by looking at it, that three portions are not equal. So we need to have a common denominator. Once we have the common denominator, then we can compare, then we can compare numerators. Simple. Then compare numerators, and when we compare numerators, greater the numerator, therefore greater the fraction. Similarly, by chance, if you have same numerators, if you have the same numerators, then lower the denominator, therefore higher the fraction. And this works in the vice versa manner as well. When I talk about a fraction, let's say 1 by 4, and I compare it with 1 by 5. 1 by 4 in terms of percentages is equal to 1 by 4 multiplied by 100, which is equal to, which is essentially equal to 25%. And 1 by 5 in terms of percentages multiplied by 100 gives me 20%. Okay, it gives me 20%. So when there are common numerators or the same numerators, then the denominator plays the role, and the smaller the denominator, the better or the bigger the fraction would be. I have very easily proved this, that 25% is greater than 20%. That means 1 by 4 is greater than 1 by 5. Okay, this is a very simple step by step process. This is a very simple step by step process that you need to, first of all, have common denominators, then compare the numerators out of them. If you have the same denominators, then you can compare the numerator. Then you can, if you have the same numerators, then you can compare the denominators and you can apply the inverse rule. Instead of simply going and saying that bigger the numerator will be happier, it will be the reverse thing in denominator. The smaller the numerator, the smaller the denominator, and you'll be happier, or you'll be larger. Got it? Moving on, I'll take you through the questions that is going to like really help you immensely. Now it says, which of the following is true? Which of the following is true? See what I do. It says 3 by 71, then 3 by 91, and it says 3 by 99. These are three options that I have. I need to see the relationship between them. In the previous case, in the previous slide, I've told you here very categorically that if you have the same numerators, then you have to focus on the denominator and apply the reverse rule. It says that 3 by 71 is lesser than 3 by 91, and it is also lesser than 3 by 99. Here, you would see that this output is wrong. You'll ask me why. This output is wrong only and only because all the numerators being same, the denominators need to be looked at, and the smaller the denominator, smaller the denominator, smaller the denominator, better the fraction. When I say better, I mean larger. So this doesn't hold true. Coming down to this, 13 upon 135 compared to 12 upon 135, 11 upon 135. Now I have three denominators which are equal. We have three denominators which are equal, and the operation which is between them is this, that 12 is greater than 11 and 13 is greater than 12. Once we have the same denominators in all of them, we are only supposed to compare the numerators. When the numerator number 1 is greater than numerator number 2 is greater than numerator number 3, this means this 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 statement number 2 is correct, and this statement number 1 is incorrect. I hope I've made myself very, very clear. Got it? Moving to the next question. This question asks me to find out the largest value of this series. Coming to the same point which I discussed over here, that I need to have common denominators. I need to have common denominators. For that, to make the denominators common, I will have to take an LCM. The LCM is the least common multiple. I will have to take the LCM, and in this LCM, there are 4, 8, 2, 5, and 5. To take this LCM, I would I'll just help you with my best shortcut. Okay, there is 1, 2, which is useful. There is another 4. So if I multiply it by 2, it is covered. There is an 8. If I multiply it by 2, the 8 is also covered. There is a 5, and there is another 5 over here. Okay, I need not use the second 5. This is very easily covered in this. So 1 5 speaks for both of them, and 3 2s speak for 2 as well as 4 as well as 8. So this is 8 5s are 40. So 40 is the LCM of this equation, of this fraction, the three fractions which I have. So the LCM is 40. Now I need to multiply this LCM with all the fractions separately. So 3 by 4 into 40, 7 by 8 into 40, 5 by 2 into 40, 3 by 5 into 40, and 4 by 5 into 40. Okay, I will multiply it by 40, multiply it by 40, multiply it by 40, multiply it by 40, and 40 again. Simple. 4 tens are 40. This gives me 30. 8 fives are 40. This gives me 35. 2, this is 100. Okay, 2 20s are 40. And 5 eights are 40. Again, another 24. 5 eights are 40. 8 fours are is 32. So I need to find out the largest value of this series. The largest value of this series is nothing but 5 by 2. This might seem to be a little um, daunting for you because you have to find out the LCM and focus on the fractions again. So I'll just give you the best way out of it. Okay. The best way says that 3 by 4 is nothing but 0.75. Why 0.75? If you go for the long division method, 4 by 3, you will put a point. You'll, sorry, 4 by 3, you'll put a point over here. You'll get 30. 4 sevens are 28. You'll get 28 over here. You'll get 2 over here. Then you'll use the point again. A 0 comes over here. And 4 fives are 20. So this gives you 0.75. This is the first first fraction. Then you have 7 by 8. 1 by 8 is nothing but 12.5. So 87.5 is the output of this, or 0.875. I should rather uh, talk about it that way. 0.875 is the output over here. If you've attended my lectures on percentages, you'd be well versed with this. 5 by 2, 5 by 2 comes out to be 2.5. The fourth one is 3 by 5. 1 by 5 is 0.2. So 3 by 2 is 0.6. Then again the fifth one is 4 by 5. 1 by 5 is 0.2. So 4 multiplied by 0.2 is 0.8. Out of all the outputs which have come, this is the largest. So that's that's all that we need to discuss when we are comparing fractions. Moving on, it asks me find the smallest number in this series. 7, 4, and 8 would go in for an LCM. 7, 4, and 8 would go for an LCM. I can simply have it in this way that 2 multiplied by 2 covers 4, multiplied by 2 covers 8, and multiplied by 7 covers 7. So 8 sevens are 56. This is my LCM. I need to multiply LCM with all the fractions that I have. I'll write down all the fractions straight away. Multiplied by 56, multiplied by 56, and multiplied by 56. So 7 ones are 7 eights are 5 eights are 40. 4 14s are 56, so 14 threes are 42. 8 sevens are 56, 7 fives are 35. Out of all these expressions that we have over here, 35 is the lowest one. So the smallest number in the series is nothing but 5 by 8. I'll help you do it with the percentage method, which I did in the last question as well. So the alternate method, or method 2 of doing this, would be 5 upon 7. Would be 5 upon 7, the first question. 5 upon 7 means 1 upon 7 is 14.28%. Okay. 14.28% when multiplied by 5 gives me somewhere around 70.14. So 71.4 is the first value. The second value, or 0.714, that is also legit. Then 3 by 4, I've already discussed. 3 by 4 is around 75%. And thirdly, we are talking about 5 by 8. 1 by 8 is nothing but 12.5. When I multiply it by 5, it comes out to be 62.5%. Okay. So this is the percentage method of dealing with this question. The ones who have learnt the fractions of what 1 by 7 is equal to, 1 by 13 is equal to, and what 1 by 9 or 1 by 11 is equal to, it's easier for them because you already have done the division in your head, and multiplication is always easier than the division. Okay, so 5 by 8 is 1 by 8 is 12.5, multiplied by 5 is 62.5. Out of the three percentages which I got, 62.5 was the lowest. That's why I could declare that 5 by 8 is my lowest and the smallest value in this series. Okay, now this is a little complicated process. We've already covered the concept which says that whenever we have a long series, in that series, the difference between the terms multiplied by 1 upon the first term and 1 upon the last term, the first term being everything on the left hand side and the last term being everything on the right hand side. Okay, it also includes it only includes the left half and it only includes the right half. Okay, there would be a few questions, upcoming questions, which would be really helpful for you. Now we'll be studying about the fourth concept. The fourth concept is nothing but cascading cascading simplification. The format would be 1 upon 1 upon x plus 1 upon y, then another plus 1 upon z, or something of that sort, and you are supposed to solve this in a ladder format, and that is how you will be reaching the final answer. There are multiple simpler ways to solve it. This entire equation would be equal to a fraction. This entire equation on the left hand side would be equal to some fraction, and with that fraction you have to find out the values of x, y, and z through the way. Okay, on the way you have to find the values, and in the end it's simply going to ask you the values of x, y, or z, or it will give you one more step of calculating, let's say, x plus y plus z. Okay, so we'll be solving this entire thing step by step, and we'll be moving to the first question. So this is the first question. It's asking me to simplify this thing on the left hand side. I will first rewrite the question for you. 1 upon whole upon 1. This 1 upon 1 doesn't mean anything, means just 1. Okay, divided by 1 plus 1 by 2 whole divided by 5. Now I'll be moving and solving it with the help of the bottom up approach. Okay, the bottom up approach. So half into 5 would be 1 by 10 plus 1 would give me 11 by 10. Okay, so we have the value of this entire expression is equal to 11 upon 10. 1 plus 1 upon 11 by 10 comes out to be 1 plus 10 upon 11. Now 1 plus 10 upon 11 gives me 21 upon 11. With the help of that, I am able to solve everything that was kept over here. Now the only thing that I'm left with is 1 plus 1 upon 21 by 11. This 21 by 11, because it is written in the denominator, it's going to create a reciprocal of its own, and the reciprocal would come out to be 11 upon 21. If I solve this, I would jump and I would reach my final answer, and my final answer would be nothing but the final answer would be nothing but 32 upon 21. All right, this is how simplification works when it is about cascading or leveled fractions. Got it? It's not very tough. If you're not able to understand, no problem. Pause the video, try to do it yourself, and then rewatch the video and learn the method. Moving to the next question, it's of a very similar nature as we've done. I'm going to solve it straight away. The only thing that you have to remember is you have to follow the bottom up ladder approach. Okay, 2 plus 1 by 4 makes 9 by 4. This 1 upon 1, I'm going to treat it as only 1. There is a plus 3 as well. This 9 upon 4, once it will go up, it would convert itself from 9 upon 4 to 4 upon 9. Now 9 threes are 27, 27 plus 4 is 31. This comes out to be 31 upon 9. The answer 31 upon 9 has solved my problem partially till this level. Taking it again to another level, this 1 upon 1 is going to be treated, this particular 1 upon 1 is going to be treated the same way the 1 upon 1 in in the denominator was treated, which is equal to 1. All right. So this 31 upon 9 stays like this. 31 upon 9, when it would move to the numerator, would convert itself to 1 upon 9 by 31. Now, upon solving this, I would be able to find out the value of the entire denominator of the full question. Okay. So this would give me 40 upon 31. Now, I'll be solving the biggest equation, which is on the right hand side of the minus. It says 5 upon 40 divided by 31. This 31 would move up. 31 into 5 is 155 whole upon 41. Sorry, whole upon 31. And there is a minus of 4 over here. There's a minus of 4 over there. So 5 ones are 5, 5 threes are 15, 155. All seems good. Now 4 multiplied by 31 would give me 124 minus 155 whole upon 31. Now this would give me the value as 31 again. 31 would be that of minus, because 155 is bigger as compared to 124, and minus 31 whole upon 31 would give me the value of minus 1 as my final answer. Okay, I hope you were able to understand it. The approach is to find out the bottommost value of the ladder, then move it up the ladder using simple basic proportionalities, solving it with the help of reciprocals. Every time you have to move a value from the denominator to a proper fraction or to a or to the numerator. Okay, so this was the entire timeline of how we made things go. Always start from the bottommost side, because that is the only thing that's going to give you a lot of pain. Okay, now this is a very interesting question. You can solve it by comparing the LHS to the RHS. And there are two ways of solving it. In the first method, I would be only working on the left hand side, so as to reach a point where the left hand side can be represented in the form of a by b. When I would compare this a by b with the right hand side, which is 5 by 8, I would be able to get the value of x. X is nothing but a component of both a and b. Okay, I'll show you how. I'll be first solving the left hand side using the very long method, which I would not recommend you to use in the exam. But you must know that this method is what should I say? It's very supreme. If you can't remember the method which I'll be using in the second iteration, you must know the first method for sure. I'm solving for this. This comes out to be x plus 1 whole upon x whole upon 1 plus 1. Okay, so this entire equation has been solved. This x goes up, it creates x upon x plus 1 plus 1. Okay, so this gives me 2x plus 1 whole upon x plus 1. Now this entire equation would again have a plus 1, and we would reach the second last level of our equation, 1 upon the entire thing. Now 3x, this is going to be 3x plus 2 whole upon x plus 1, and this entire thing is in the numerator. And we have solved the left hand side. The output of this left hand side is going to be x plus 1 whole upon 3x plus 2. Okay, x plus 1 whole upon 3x plus 2. This is 3x plus 2. Now this 3x x plus 1 whole upon 3x plus 2 is nothing but 5 by 8. This is nothing but 5 by 8. Yeah. Yep, it seems so. No, this x plus 1 shouldn't be x plus 1. It should at least be 2x plus 1. I will recheck my question over here. Okay. This x plus 1, 1 plus x plus 1 would give me 3x plus 1 whole upon 2x plus 1. Hmm. This this entire equation of 2x plus 1 should have been here. Just give me a second. I'm going to redo this because I feel there is a very small error that has been committed. And this error is going to be useful for everybody because in the exam there is a good possibility that you also commit the same error. Okay, I'll change my the pen color. So 1 upon x plus 1 has been converted to x plus 1 upon x, and it is written over here. This entire thing comes down to this. This gives me an output of 2x plus 1 whole upon x plus 1. This 2x plus 1 whole upon x plus 1 is supposed to be created into a reciprocal first. Okay, because this entire story is set up in this method. This entire story is set up in this method. This should have been the case. Okay, I hope you can see where the fault was, and it's going to be pretty helpful to all of you. This gives me an output of 1 upon x plus 1 whole upon 2x plus 1. Now the output of this is going to be 3x plus 2 whole upon 2x plus 1. This entire story is now in this manner: 1 upon 3x plus 2 divided by 2x plus 1. This entire story, being in the denominator, has to be brought to the numerator. So 2x plus 1 whole upon 3x plus 2 would give me the value of 5 upon 8. And further, if now you try to put in a value of x, you can use these directly. You can use the options directly. But if you put the value of x as 2, we'll be able to find out that 2 2s are 4, 4 plus 1 is 5, and 2 3s are 6, 6 plus 2 is 8. So this gives you that the value of x is equal to 2. Now this is the longest method that you would ever encounter to solve this question. This cannot be done within a minute, but my second method, can definitely take us to a point where we can solve this entire question in a minute. We won't be needing a lot of space to solve that. We have 5 by 8 on the right hand side, and I need to break down this 5 by 8 to a level where my final division comes down to 1 upon 1 by x format. 1 upon 1 by x format, and there has to be the point of reciprocal which is happening multiple times. Okay, I'll show you how. We have 5 by 8 on the right hand side. Let's flip it to 8 upon 5. Let's take it to a mixed fraction format where this comes out to be 1 plus 3 by 5. Right, now we have 3 by 5. Let's flip it to 5 by 3. The 5 by 3, let's now move it to the mixed fraction format. The 5 by 3 in the mixed fraction format is 1 upon 2 by 3. 1 upon 2 by 3. Now let's move it on and take 2 by 3 outside. 2 by 3 outside has to be flipped to the 3 by 2 format. Now let's create it into a mixed fraction format. The mixed fraction format says that 1 upon 1 by 2 would give me 3 by 2. So now you have my attention, and now you know the final answer. The final answer is 1 upon 1 by 2, which needs to be compared to 1 upon 1 by x. When I do that, I find out that 1 plus 1 upon x is equal to 1 plus 1 upon 2 when I have the first question as well as the first remainder, or the last question or the last remainder equal to 1. That is when I find out the value of x. In a mixed fraction, it's nothing. Everything that comes outside the plus sign is the quotient, and whatever remains in the numerator is the remainder. So the value of x from this basic proportionality, the value of x comes out to be 2. You won't have to follow this entire, you won't have to take out your arsenal to fight this question. If you focus on the right hand side, flip it, flip it and split it. Okay, so this is the method, flip it first, then split it. So that is how you reach the conclusion that 1 plus 1 upon x is going to be my output. Okay, so that was concept number 4. We'll be moving to concept number 5 in a short while. So now we're talking about concept number 5 of simplification. In the fourth concept, we've already learned that LHS has to be equal to RHS, where we have to constantly flip the RHS so as to get all the numbers which are there in the LHS. So the similar concept is going to turn up over here. This is the first simplification concept. It says 1 minus 1 whole upon 1 divided by 1 minus 2 by 3. Let's start from the bottom. 1 minus 2 by 3 gives me 1 by 3. When 1 by 3, I'll just change the color of the pen. When 1 by 3 moves over here, it's going to convert itself into 3 by 1. So this entire portion would be rewritten as 1 upon 1 by 3. So it's basically 3 by 1 over here. Then again, 1 minus 1 by 3 would be written as 2 by 3, which is the final answer. This is pretty simple. We are not using a lot of brains over here. A simple mechanical calculation is going to get you to this answer. Moving on to the next question. Similar thing is going to happen over here. We are going to start from the bottom. 4 minus 1 by 4. So 4 4s are 16. 16 minus 1 is 15. So 15 by 4 once reciprocated or once reciprocaled would give me 3 minus 4 by 15. I hope you get this thing really well. Okay. 3 minus 4 by 15. Now 15 threes are 45. 45 minus 4 is 41. It's 41 upon 15. In this bigger equation, again, there's going to be another reciprocal. This reciprocal is going to turn out to be 2 minus 15 upon 41. Okay. 2 minus 15 upon 41. Doing it again. 41 twos are 82. 82 minus 15 is 77. 67. Okay. So 67 upon 41 is going to come over here in the entire equation. Now we've reached the final point. Okay, now we've reached the final point. 67 upon 41. This 1 upon 1 I'm going to write as simply 1, and there is going to be a plus sign over here and a 2 over here. Okay, again another reciprocal is required. So 2 plus 41 upon 67, this is going to give me my final answer. 67 into 2 is equal to 134 plus 41 whole upon 67. This would lead to the final answer as 175 upon 67. Okay, so I hope you understand how we take the bottom up approach, and every time we have a fraction of the nature 1 upon a by b, we write it as b by a simply. Let's assume we have an equation in the form of a by b upon c by d. We will be writing this as a by b multiplied by d by c. Okay, this would convert itself into AD upon BC. Okay, AD upon BC. This is the very standard form of equation that we've already talked about. If you didn't get it much, no problem. You can learn it from here itself. Okay, moving ahead. Now, this is the same long form thing which we've done, but the number on the right hand side needs to be equal to everything on the left hand side. Every time we'll be flipping the right hand side so as to achieve a quotient, and that quotient would be equal to the the variables on the left hand side. Okay, the first variable, the second variable, and the third variable. Okay, so let's see how it actually works out for us. So we have 29 upon 79. It would flip to 79 upon 29 first. Then we will have 29 twos are, that's 58. 58 and 79 have a gap of 21 in it. Okay, So 21 upon 29. So this value of 2 is equal to the value of x. Moving to the next point, we have 21 upon 29. We would create a reciprocal of it. So it's going to be 29 upon 21. Now on 29 upon 21, we are going to apply the same operation as we did over here. We are going to convert it into a mixed fraction as compared to the complete fraction that is available over here. This is actually an incomplete fraction because the numerator is more than the denominator, but we'll anyhow work on it. So 21 ones are 21 plus 8 upon 21. Okay, so here we have achieved the value of y. Now to achieve the value of z, what's going on you must see over here. We have 2 upon z plus 1 by 4. Our method of flipping and creating a quotient works every time there is a 1 over here. It always works in those cases when there is x upon 1 upon y, or when there is y plus 1 upon z. As we already have a 2 in the numerator, I'll just change the color. 2 in the numerator means at this point, we are talking about this 2. Had this been a 1, it would have been to our support. But it is a 2, so whatever we are going to work on next, which is equal to 8 upon 21, let us flip it first, or let us divide it by 2 first. 8 upon 21 divided by 2, or let's multiply it by half, which is equal to division by 2. So this would give me 4 upon 21. Now I have to work upon 4 upon 21. And how do I work that out? So it is 21 upon 4. I first make a reciprocal out of it. Then I convert it into the mixed fraction format. 4 5s are 20 plus 1 by 4. Now, as you can clearly see, this 5 plus 1 by 4 is giving me the same feeling or the same format as z plus 1 by 4 is giving. Okay, so z plus 1 by 4 is equal to 5 plus 1 by 4. So from here, I can gather this thing very clearly that the value of z is nothing but 5. I've gotten all the three values. The value of x from this portion is equal to 2. The value of y from this portion is equal to 1. And the value of z from this portion, which we just solved, is equal to 5. What do I need to find out? I need to find out the value of 2x plus 3y minus z. Okay, so 2x is equal to 4 plus 3y is equal to 3 minus 5 is equal to z. 4 plus 3 is 7. 7 minus 5 is 2. So 2 is my final answer. Okay, are we clear with that? I hope we are. No problem, you may re-watch the question to go ahead. Now, we again have a similar problem over here, which we just solved. So we are going to follow the same approach, and I'm going to be just a tad bit like slower on this, okay? So as to help you understand what we are going through. We have 45 upon 53. All the equation formats are based out of 1, so it's not going to be a problem for us. We won't have to apply any special logic which we applied for z over here. Okay, we employed a special logic for z over here, so we won't have to do that over here. 45 upon 53, I will flip it in the first go. 53 upon 45. Now moving ahead, converting it into mixed fraction. 1 plus 8 upon 45. That's my first step. Okay, that's my first step. So this gives me the value of a. Moving ahead, I need to talk about 8 by 45 now. 8 by 45 would be reciprocal into 45 upon 8. Then converted into mixed fraction. 8 5s are 40. 8 5s are 40, and another 5 upon 8. This is where I reach the value of b. Now, I am left with 5 upon 8. I would reciprocal it. And now, there is a very special catch I have to talk about over here. The c has something subtracted from it. What I have over here is 8 upon 5. What I have over here is 8 upon 5. I can convert it into c with 2 in 2 areas, okay? This can be done as 1 plus 3 upon 5 or 2 minus 2 upon 5. If I follow 1 plus 3 upon 5, my output is going to be 8 upon 5. which is where I'm starting the question from. Similarly, if I convert it into 2 minus 2 upon 5, it is going to convert itself into 8 upon 5 again. Okay, but this format of the equation of 2 minus 2 upon 5 very clearly matches c minus 2 by 5. This is following the rule which I am looking for. So c minus 2 by 5, if I use this, I can easily get the value of, and I match the terms. C minus 2 by 5 is on one side and 2 minus 2 by 5 is on one side. So this clearly indicates that my value of A is equal to 1, my value of B is equal to 5, and my value of C from this equation is equal to 2. What have been asked is 4A plus B plus 3C. So the value of A is 1, so 4 into 1 plus the value of B is equal to 5, so that's 5 over here, plus 3C, 3 is equal to 2, so 3 into 2 is equal to 6. So 4, 5, 9, 9 and 6 is 15. So my final value of this question is going to be 15. All right, so let's move on. Another very similar question, and it's asking us to follow the long division method. See, whatever I have been doing over here, we've been flipping, we've been reciprocating whatever we have on the right hand side. Now I'll tell you a simpler way and maybe a longer way. People, it depends from person to person how they like it. I just need to record the quotients. Okay, my method is going to be record the quotients, and that's how I will reach my area. All the quotients would be written over here on the right hand side, okay, of the long division method. 13 by 29. I have already taken a reciprocal of it and written 13 by 29. So 13 twos are 26. Here I am left with a remainder of 3. This would be continued division with the last divisor. Okay, so 13 would go here. 13 fours are 12. Sorry, 3 fours are 12. This is 2. This is 12, and I'll get 1. Then the older divisor back inside as the dividend. So 1 3 is a 3. This is going to be 3, and this is come down to 0. I have to reach a point where the last remainder is 0 or full division has been achieved. As soon as I get the remainder as 0, my full division has been achieved. The first quotient has been recorded, the second quotient has been recorded, and the third quotient has been recorded. So as we are moving in the sequence A, B, and C, these quotients are also in the same sequence A, B, and C. So the value of what has been asked over here is 2 minus 4 plus 3. This gives me the value of 1 as the answer. This is my final output. Now we'd be moving to concept number 6. The only thing which is distinct between concept number 4 and concept number 6 is this, that the signs are now flipping. The signs are now alternating. So I have to take care of these signs. I have to alternate on them. No problem. We will follow our own standard, our own long form work. And trust me, it is going to be very helpful to us. Solving it here from the bottom, 1 plus 1 upon 1 by 3. This would give me 1 plus 3, that is equal to 4. So this is my output. 1 minus 1 by 4, and this is my solution till this point. 1 minus 1 by 4. 1 minus 1 by 4 is equal to 3 by 4. Now this 3 by 4 would be flipped into 4 by 3, and there would be a plus 1 sign over here because we've reached this point now. Okay, I'll point out the areas where we've reached. When we were solving this, we were solving the first plus where we got the value 1 by 4. Then when we solved for 3 by 4, we got the value till point number 2. This minus sign indicated 3 by 4. This is point number 2. Now we are again solving for plus. This is point number 3 where we are solving. 1 plus 3 by 4 is nothing but 7 by 3. 1 plus 4 by 3 is nothing but 7 by 3. This is the third point what we've achieved. Okay, this is the third point, the output of the third point. These 2 points are the same. Now there is a minus in there's a minus over here, and I need to flip it. So 1 minus 3 by 7. This is what I have achieved, and this is point number 4. All right, this is point number 4 where I have reached. 1 minus 3 by 7 is 4 by 7. Okay, it's 4 by 7 and I have achieved the output of point number 4. Now reaching point number 5, which talks about plus. So 1, and I have also have to flip it. 1 plus 7 by 4 is my output, and the final answer comes out to be 11 by 4. So this is my final answer. Okay, the only difference is that there are alternating plus and alternating minuses which we need to follow. Moving ahead, this is a little long in terms of fighting for the answer. Okay, so I'm going to cut it down. I'm going to cut it down into pieces. This is the first piece of it, this is the second piece of it, and this area is the third piece of it. Okay, so how could I do that? Because I could see that this is an important operation over here. Secondly, the the round braces are here and the round braces are here. So I could split one entire question into three almost equal parts. So what I'll do is I'll solve it as soon as possible for the rightmost side first. Okay, so there is 4 plus 3 divided by 0.5 minus 1. This would solve using the BODMAS. We'll solve using the BODMAS method. 3 divided by half, or 3 multiplied by 2, gives me 6. 6 plus 4 minus 1 gives me a 9. Okay, so the third portion of the equation has been solved and the value of that thing is 9. Now talking about the second portion of the equation, it says 12 ones are 12 and 17. It says 17 upon 12. Off means multiplication and it is of a higher degree. Off needs to be solved before the division. Okay, it says BODMAS, BODMAS. So O stands for off and O also stands for order. So O needs to be solved first as compared to the division. So 17 upon 12 multiplied by 72 upon 145. Okay, 72 upon 145. So 12 ones are 12, 12 6 are 72. I would let this thing remain in its most natural form. It means 17 multiplied by 6 whole divided by 145. This is my output for my second point. I have achieved the third point, I have achieved the second point. Now I would move to the first point. The first point seems to be a little long. So what I'll do is I will use a different pen. I'll do it here itself. 2 plus 4 by 3 is 4 2s are 8. 8 plus 3 is 11. 11 by 4. 11 by 4 flipped would give me 1 minus 4 by 11. Okay. So this portion has been solved. Now I'm talking about the minus portion. 1 minus 4 by 11 gives me 7 by 11. 7 by 11 is the output of the minus that you can see over here. Now I will solve it for plus, and there is a numerator of 2 as well. When I flip it, I have to flip it once. The 11 would go in the numerator. The 11 when multiplied by 2 would give me 22 upon 7. Would give me 22 upon 7, and I have to add a 1 over here. That would give me the answer as 29 upon 7. This 29 upon 7 has given me the output of this plus. Now there is a minus sign over here. 4 minus 2 by something. This something which I have talked about is 29 by 7. It needs to be flipped and then multiplied by 2. So if I flip it, it's 7 by 29. When I multiply it by 2, it is 14 upon 29. This 14 upon 29, this would basically be 4 minus 14 upon 29. 4 minus 14 upon 29. Now I would give you a shortcut of solving this 4 minus 14 upon 29. 4 into 29 is nothing but 116. How could I reach that? Because 430 is a 120. When I multiply 4 by 30, it gives me 120. 120 minus 4 would give me 116. So 116 we have here, 116 minus 4 upon 29. This 116 minus 4 is going to convert itself into 112. 112, no, that's not 4, this is 14. This 112 is nothing but 102. Okay, 102. 102 upon 29 is where I will reach. Now, this is my output of my first portion. Let me put things back into perspective. It is 102 divided by 29. There is a division sign over here. The division sign says that 17 into 6 is going to be here and 145 is going to be here. Then in the third portion, we have a minus sign. This minus sign gives me a value of 9. This minus sign gives me a value of 9. So simply going ahead, 102 upon 29 division would convert into multiplication if we have the right hand side as reciprocal. This would give me 145 upon 17 into 6, and this again gives me minus 9. Let me solve it with a different pen color. It's going to be quicker for you. 29 ones are 29 fives are 17 6 are 102, and 102 is cancelled over here. So 5 minus 9 would give me an answer as would give me the final answer as minus 4, and that is my option over here. That is my option over here. So this was everything that we've done, split up into three parts, and then getting all of them back together at this point. Okay, this is the first the portion we solved. This is the second portion we solved, and this is the third portion we solved. And we brought all of them back together over here in this equation. Anytime you get this question, please at least leave 2 minutes to conceptualize and 2 minutes to formalize this thing and 2 minutes to materialize the answer of this question, because it's a little long. It's not difficult, it's a little long. So please do it in the end. Do not do it in the at the beginning of the examination. Coming down to the next simplification concept, this is going to be similar. The only difference is that we have to talk about decimals over here. Okay, we have to talk about decimals over here. Whenever we are adding up decimals, okay, whenever we are adding up decimals, let's assume 1.007 and we are adding it up with 2.7. So what would happen is we need to equalize the decimals. We need to equalize the decimals. When I say 1.007, this has 3 decimal places on the right hand side. When I talk about 2.7, this has only 1 decimal place on the right hand side. To equalize these two in terms of the decimal length, what I'll do is I'll add 2 zeros in the end. Okay, so this doesn't change the real value of 2.7. You can say 2.700, 2.75 times 0. So that all comes down to 2.7 only. So you need to learn that you have to equalize the length of the decimals whenever you're adding or subtracting. It's not subtracting, it's subtracting only. Okay, whenever you're adding or subtracting, you need to equalize the length of the decimals. So when I add it up, it comes out to be 3.707. Had this been a question, and the final answer is 3.707, it hardly depends on whatever decimal places were there in the beginning. You have to equalize the decimal places. So the more decimal places you will get on the right hand side, the longer the answer would be, or that would be equal to the final answer which you get on the in the end. Okay, so adding and subtracting, the decimal places need not be like need not be worried about, because you simply have to equalize them. Similarly, when I talk about multiplication, what we do is, let's assume the same thing. 1.007 has to be multiplied by 2.7. So the sum of the multiplication decimals, here the multiplication decimals, the length is 3. Here the multiplication decimal, the length is 1. So the sum of the multiplicating decimals would be 4, right? The number of decimals which we'll get in the output is going to be 4. So I'll simply multiply 27 multiplied by 1007, and whatever answer I get, I have to put 4 decimal points in that. Okay, I'll quickly solve it for you. 7 7s are 49, 7 2s are 14, 189, and 27,000. So 27,000. This answer is 189. This is 27189 with 4 decimals in it. So 1, 2, 3, and 4. So 2.7189 is my final output. when I'm multiplying the decimals, or whatever places are there on the right hand side of the decimals, they would add up and they would show up back in my answer. Talking about division, what happens in division is that 1.007 is divided by 2.7. So 1.007, this decimal can be removed and three zeros or 1000 can be placed in the opposite side of it. If it is there in the numerator, the thousand or the tens or the hundreds would be placed in the denominator. And here, this one decimal needs to be removed. So 10 would come in the numerator. I hope you get it very well. After solving this, let's assume that we find the answer as A, B, C, and D. So 10 is cancelled with 10. We are left with two zeros, or we are left with 100 in the denominator. This 100 would give me two places of decimals, and my final answer would not remain ABCD. My final answer would come out to be AB dot CD. My answer would come out to be AB dot CD. So these are the fundamentals that you need to know whenever we are solving questions with decimals in it. Okay. So these are the fundamentals that you need to know. Moving ahead, 7.5. Again, we are going to split this question into multiple parts. Let's solve this question, this portion first. Why? Because it is covered with round brackets. So 54 or 5.4 divided by 4 minus 5 multiplied by 2. So 5.4 divided by 4 can be written as 54 upon 10. The division by 4 can be written as multiplication by 1 by 4. So 2 2s are 4 and 2 27s are. This gives me 27 upon 10, 27 upon 20. This gives me 27 upon 20 minus 10. 27 upon 20 minus 10. Okay, I'm overcomplicating the things, I know very well, but it is very much required. Trust me on that. Let me simplify it down a little. Is it required? No, I don't think so. So let this be the first portion which we've solved. Let's talk about the second portion. The second portion says 8 into 4 divided by 3.2. Using BODMAS, I know very well that 4 needs to be divided by 32 first. This 3.2 would convert itself into 40 over here. The 10 would go up, and this thing would be multiplied by 4. So 8 ones are 8, 8 fours are 32, and 4 tens are. So the output of my second portion is 10. Now the third portion that I'm talking about is simply 7.5. So I'll rearrange things back. 7.5 plus 27 upon 20, 27 upon 20 minus 10 minus 10. Okay, 27 upon 20 minus 10 minus 10. This minus 10 and minus 10 will become minus 20, and let us have it over here like that only. 27 upon 2, 27 upon 2 would give me 135 or 1.35. So this 1.35 that I would get, 27 upon 2 is 13.5. 13.5, another decimal would shift to the left because of the 0 that I have here. So 1.35 is here, minus 20 we have here. This thing is of plus, and there is 7.5 over here. This 7.5 can be written as 7.50 because of the decimal. This 20 can be written as minus 20.00 because of the decimals. Now I have all the decimals in place. I can very easily write it as 8.85 minus 20.00. This minus 20.00 would finally give in and come out as 15, like 0.15. And when 20 is subtracted out of 8, it will give me 12. But because there is a decimal and carry forward, my final answer would come out to be 11.15. Okay, so 11.15 is my final answer. Moving ahead, just take care a little about the decimals and everything else would take its own shape. I have 21.6 divided by 3.6 at first, then the entire equation is multiplied by 2. Look how smartly I did everything over here itself. I know that division has a higher precedence, so I would let that solve first. 1.25 multiplied by 16 divided by 4 and minus 6. Quickly solving it, 4 ones are 4, 4 fours are 16, 425 is 100. There are two decimals already, so 100 would come out as 1.00. Again, 36 ones are 36, 36 6 are 216. The decimals cancel out each other because they're of the same length. So 6 twos are 12 comes out as 12 plus. And then there is a minus 6 over here. So 12 plus 1 is 13, 13 minus 6 is 7. So 7 is my final output of this complicated looking question. So look how quickly we can get out of such situations. Okay, just take care of the decimals and keep the BODMAS order in your head very well. Coming to the next question. Again, take care of the decimals and everything else shall take care of itself. There is 5.8. There is a division sign which comes at first. There is 2.9 multiplied by 2 minus 3.5. Then another multiplication by 2 whole divided by, because this division is over here, this would come out as 0.5. Solving it from the right hand side to the left hand side, the decimals would get cancelled out. 5 sevens are 35, 7 twos are 14, minus 14 comes here. 29 ones are 29, 29 twos are 58, 2 twos are 4. The decimals would take care of themselves, plus 15.2. Now 15.2 and 14, they have a gap of 1.2 within them. 1.2 plus 4 would give me 5.2 as my final output. Okay, so concept 7 is done with. We just have to take care of the decimals wherever they land. Okay, decimals wherever they land, the addition, the subtraction, the multiplication and the division has been discussed, and I've taken you through 3 of my good questions which have already appeared in the examination. Now we'll be talking about recurring digits of the recurring digits in fractions. Okay,
We are now at concept number 8. In concept number 8, we have a very standard practice that we are going to check, which is called denoting fractions with the help of bar. What happens is there are some fractions or some numbers which are terminating in nature, and there are some fractions which are non-terminating in nature. What do we mean by terminating? When I say terminating, let's assume I said 2 by 5. So when I divide 2 by 5, my final answer comes out to be 0.4. And this is where the division between 5 and 2 ends. Okay, so 5 and 2 ends here by giving me the result 0.4. But had this denominator not been 5 but been 9, 2 by 9, so what would happen is, I'll show you with the help of long division. Here it is 9 on the outside and 2 on the inside. The dividend is 2. So 9 point, the point would come here, this would become 20. 9 twos are 18. I have another 2. The point would again secure a 0 for me. Then again 9 twos are 18. Then again a 2. And this story goes on. Okay, so 0.22222. This goes on like this. So this is when I talk about non-terminating decimals. Okay, so a fraction which repeats itself, repeats a part of it itself or its entire self, that is called a non-terminating fraction. And when I talk about 0.2 bar, this is equivalent to 0.222 till infinity. Okay, and when I need to represent 0.2 bar in the form of a fraction, so what I would do is, I would, the number of digits which are under the bar would be represented by nines, and the number of digits which are not under bar would be represented by 0. I'll help you first with this. Let's assume there is only one number which is under the bar, so the answer would be 2 by 9. I'll help you with this.
let's assume that x is equal to 0.2 bar. If I multiply it by 10 on both sides, then the value of 10x would become 2.2 bar. Let me subtract the first equation from the second equation. So 10x minus x gives me 2.2 bar minus 0.2 bar. This entire exercise was carried out only and only to eliminate the bar from this question, only to eliminate the non-terminating thing in the equation. So 2.2 bar minus 0.2 bar gives me 2 as my final answer. So the bone of contention, or things which you don't like, the bar is no more there. The answer is 2.0 over here. And 10x minus x is equal to 9x. So the value of x is nothing but 2 by 9. And I've already talked about the shortcut. The shortcut says that every digit under the bar would represent a 9, and every digit outside the bar would represent a 0. Okay, I'll give you one more example. Let's assume 0.456 and the bar is only sitting on 56. Okay, the bar is only sitting on 56, and somebody tells me to convert this fraction into to convert this non-terminating decimal into a proper fraction. So what I would do is, simply I would write 456. The things which are under the bar would give me 9 each. So there are two digits under the bar that would give me 99, and there is one digit outside the bar which is 4. So that would give me a 0, and there would be a minus sign over here. What would this minus sign represent? This minus sign would have the digit which is outside the bar. So 456 minus 4. When I finally write it down, I would write down 452 divided by 990. Okay, I'll write down 452 divided by 990, and this would be my fraction format of 4 point of 0.46 0.456 with a bar on 56. If you'd like to know the derivation, then hold on to your seats. I'll show you the derivation of this. Let's assume the value of x to be 0.456 with a bar on 56. Let there be 100x. Let there be 10x first, okay? Let there be 10x first. The 10x says that 0.56, the 56 gets a bar over here. Now, as 56 is occurring multiple times, then I would have to, as 56 is occurring multiple times, I will have to multiply this this first equation with 100, because 56 is occurring, okay? 56 is occurring in a pair. So I would need 100 times of this. That means 1000x would be required to remove the 56 out of the bar situation. So it would be 456.56 bar. This becomes my second equation. Okay, now we are in a position to eliminate the bar. Okay, now we are in a situation to eliminate the bar. What I would do is equation 2 minus equation 1. It would give me 990x is equal to 456.56 bar minus 4.56 bar. This bar and the other bar would now get cancelled out, and 456 minus 4 would be my answer. That would give me 452, and there is a 990x over here. So the value of x would finally come out to be 452 upon 990. Need not follow this long approach in the examination unless you forget it. There is a better way out, which I have already told you. Okay, I'll repeat the better way out. The number of digits under the bar, which are 56, would be represented by nines, the same number of nines, and the digit which is outside the bar would be represented by a 0, which I have already written. So 456 minus the digit which is outside the bar would come here, and 990 would remain over here. So 452 upon 990 would be my answer. Similarly, 0.2 bar in terms of a fraction can be written simply as the number of digits under the bar is 1. So a single 9 can suffice. So 2 upon 9 would be my answer. Moving to the real world questions. It says if n is 0.369369 and so on, and m is 0.531531, then what is the value of 1 upon n and 1 upon m? If we have the value of n as 0.369 bar and we have the value of m as 0.531 bar, okay, these are bars only because they are repeating in couples of 3, in tuples, not couples, tuples of 3. Okay, so these are basically triplets because 3 digits are repeating. So when these triplets are appearing, I need to convert 0.369 bar into a fraction format because they have asked me the answer in 1 upon n form. So 0.369 can simply be written as 369 divided by, now there's 3, 6 and 9. All the 3 digits are under the bar. So for each and every digit under the bar, I'll use 1999 over here. All right. All right. So there is 111 and there is 41. This gives me the answer. Oh, this gives me the answer as 41 upon 111. Similarly, for m 0.531, there's a bar over here. To remove all the digits under the bar, I would use one digit 9 each. So 999 and 9 triple ones are, and 9 fives are 45 and 9 nines are 81. This comes out to be 59 by 111. 59 by 111. Now I simply have to flip them. Flip them means 111 upon 41 plus 111 upon 59 and add them up. 111 would be taken as common. 59 plus 41 would give me 100, and 59 multiplied by 41 is something I would have to do. So this gives me the answer 11100 multiplied by 59 into 41. 59 into 41 can be written as 50 plus 9 minus 9. 50 plus 9 multiplied by 50 minus 9, which can be written as a square minus b square. A plus b, a minus b is equal to a square minus b square. So that is equal to 2500 minus 9 nines are 81. This would give me 2419 as my answer in the denominator. So 11100 upon 2419 is my final answer. Moving ahead, there's another question, a very beautiful question. Okay, we'll solve things separately and then we'll bring it to light. There is a 46 over here. To remove the bar from 6, we will have to bring a 9. To remove, and there is one digit which is outside the bar's purview. So 9 and 0 over here. There is supposed to be a minus 4 because 4 was not under the bar. Coming down to the next point, it says 723. We'll bring 723 to the light. Then 2 digits are under the bar, so there is going to be a 99. One digit is outside the bar, so there's going to be a 0. There needs to be a minus, and the minus digit is supposed to be the digit on the right hand side of the minus is supposed to be the digit which was outside the bar. 723 minus 7 minus, I have 0.39 and I have 0.7. The 39 has a bar on 9, so I'll be removing these dots. Okay, I'll be removing these decimals. 399 has a bar on it, so 9, and 3 doesn't have a bar on it, so 0, and minus 3 needs to be done to finalize this point. Okay, then 0.7 bar, there is a bar on 7, so a 9 would come here. I would simplify the rightmost direction first. It means 36 upon 90 multiplied by 7 upon 9 minus 716 upon 990 plus 42 upon 90. Now just see where I'm headed to. 9 ones are 9, 9 fours are 36, 4 sevens are 28, 28 upon 90 is a negative term, 42 upon 90 is a positive term, and 716 upon 990 is another positive term. I would solve these two questions first. So 42 minus 28 gives me a 14 upon 90 plus plus 716 upon 990 is my final call. To create 14 upon 90 into, like, to ease down on my calculations, what I would do is I would multiply an 11 in the denominator and an 11 in the numerator. So 11 into 150 into 14 is equal to 154, and 990 into 11 is equal to 990 plus 716 whole upon 990. These two 990s would, like, the bases are common, so 990, it would ease down on my calculation. So it would come down to 0 and 7 870 upon 990. I'm bringing this answer outside. Okay, I'm bringing this answer outside. So 870 upon 990, this is my final answer. I would cancel out these two, as again we have two nines in the denominator, like 99 in the denominator. That means a bar needs to be set, and the bar would be set on the numerator. So a point would come here, and 87, both the digits would come under the bar. My final answer would come out to be 0.87 bar, and the correct option is 0.87 bar, which is correct option is option D. All right, moving down to concept number 9 of simplification. Before introducing you to concept number 9 of simplification, there are a few standard identities which I and all the examiners across all the different examinations would expect you to know. Okay, so these are the simple algebraic identities which you need to know. You've already learned them in school, but I'll be, like, helping you revise them today. A plus B in a whole square format. This comes down to a square plus b square plus 2ab. Similarly, a minus b whole square is a square plus b square minus 2ab. If I um, if I would like to, like, add both of them together, I have an option of writing it down as a minus b whole square, and there would be a plus 4ab over here, and this can be written interchangeably as a plus b whole square minus 4ab. These two identities would be used a little less in frequency, but these two full-sized identities would be used a little more frequently. Moving ahead, there is an identity of a square minus b square, which when expanded comes out as a plus b multiplied by a minus b. Okay, this is a very frequent identity, and you must know all of them, the first one, second one, and the third one. Then there is an identity where you can add up both of these, which would give you as a plus b whole square plus a minus b whole square. So when you add both of these things up, the minus 2ab minus the plus 2ab and the minus 2ab, they get cancelled out, and what you are left with is a square plus b square whole multiplied by 2. Okay, this is nothing but a derivation of these two identities. There's a third derivation of these two identities, that is a plus b whole square minus a minus b whole square. Okay, so here the output what you would get is 4ab. 4ab. So these are just the derivations of whatever we've learned here. These first three are the standard identities, and everything here, like this 1 and 2 and this 3 and 4, what we are seeing right now, are the derivation of the identities that we are talking about. Now coming to the bigger identity, which involves three variables. the identity is a plus b plus c whole square. This identity comes out to be a square plus b square plus c square plus 2ab plus 2bc plus 2ca, and I would be writing them down as ab plus bc plus ca. Okay, 2ab plus 2bc plus 2ca. This would be the final outcome. Then I can also take it to the cube side, a plus b whole cube. A plus b whole cube would give me the answer as a cube plus b cube plus 3ab, a plus b. There is another way of writing it, a cube plus b cube plus 3a square b plus 3ab square. Okay, this is nothing but the same thing, just a more expanded form of what I was talking about previously. Then there is an identity of a minus b whole cube. This a minus b whole cube identity stands for a cube minus b cube minus 3ab multiplied by a minus b. When I expand it properly, I would get as a cube minus b cube minus 3a square b plus 3ab square. Okay, nothing but the expanded format of the same. This identity is sometimes very useful for these examinations because it is a identity which is used very less. A minus b whole square plus b minus c whole square plus c minus a whole square. This would come out as 2 times a square plus b square plus c square minus ab minus bc minus ca. Okay, this is a star identity. You must learn it by heart. Okay, you must learn it by heart. There are no there are like there would be very long derivations to these identities, so I would recommend that all of you just learn them by heart. Then another very good and standard identity is that of a cube plus b cube, and the identity starts from here, a plus b multiplied by a square plus b square minus ab. Another one of a cube minus b cube, this would be a minus b multiplied by a square plus b square plus ab. Okay, so these are all the main identities which we would be using in the upcoming questions, and these are the standard algebraic identities which you must learn by heart. Okay, moving ahead. So just see very carefully where we are and what we are talking about. It says there is a number whole cube and there is another number whole cube. Let's assume that this is a and let's assume that this is b. So the question says a cube, the question says a cube plus b cube whole upon, if you look very closely, this is a square, this is b square, and this must be ab. Okay, so it says a square plus b square minus ab. So if I multiply a plus b on both the sides, the denominator would be equal to an identity which we just learned over here, this identity which I just put an arrow on, a cube plus b cube. This is the same identity, so the entire denominator would get cut off and I would be left with a plus b. Over here, what is the value of a plus b? The value of a plus b is 2.53 plus 2.47. This would give me the value as 5. Okay, this would give me the value as 5. So this entire expression is nothing but 5. Okay, this entire expression is nothing but 5, and there is no minus 1. Okay, I just got a little tricky. Okay, so this has a minus 1 over here. No. Okay, so there's a catch over here. Okay, I'll tell you there's a catch over here. The catch over here is this, that everything in the numerator, in the numerator is in the form of 2.53, and everything in the denominator is in the form of 25.3. Okay, everything is in the form of 25.3 in the denominator, so there is a gap between the between the decimals of the numerator and the denominator. If I try to fill that gap would come out to be 253 upon 100 because of the numerator, and 253 upon 10 in the denominator. These two 253s would get cancelled, and this 0 would get cancelled by 0. So there is a factor of 1 by 10 which needs to be multiplied to the final answer. The final answer in this case is 5. So 5 multiplied by 10 would give me 5 multiplied by 10 raised to the power minus 1. So it says that the value of this entire expression is 50 into 10 raised to the power k. Okay, it says 50 into 10 raised to the power k. 50 into 10 raised to the power k. This is equal to 5 into 10 raised to the power minus 1. Okay, if I need to find out the value of 10 raised to the power 5k, I'll have to cancel the 5 on both sides. This 0 comes out to be 0. This 0 goes down and creates another 10 raised to the power minus 2 over here, and then there is 10 raised to the power k. So the value of k, as the bases are same, the powers would be equal. So the value of k comes out to be minus 2. So the value of k is equal to minus 2 in this equation. I would repeat the question because some of you might have gotten bulldozed by the question. The question says that a raised to the power cube plus b raised to the power cube, and everything which is written in the denominator is equal to the entire standard format of this identity is available: a cube plus b cube whole upon a square plus b square minus ab. Okay, so let us put it away. This comes out to be a plus b, and this also comes out to be a plus b. I am multiplying it by the numerator by a plus b and the denominator by a plus b because the denominator contains an identity, and to fulfill that identity, a plus b is required. When this identity comes into play, this entire denominator gets cut off by the major player in the numerator. So I'll be left with a plus b. That is the reason I am multiplying and dividing by a plus b. That was the main catch of this question. Now it's asking me to simplify p cube plus 27. We know that 27 is nothing but p cube. So I can write down p cube plus 3 cube. Let me extend it. P cube plus 3 cube can be expanded in the form of a cube plus b cube, which is equal to a plus b multiplied by a square plus b square minus ab. So I would be expanding it as p plus 3 multiplied by p square plus 9 and minus 3p. So this is it. This is how my expansion works. Okay, and this is my final answer also. Moving on, it again is asking me a very similar question, and I would be using the identity a plus b multiplied by a minus b, which would give me the output as a square minus b square. Okay, we'll be using it twice. 6p plus 7q multiplied by 6p minus 7q. This would give me the answer as 36p square minus 49q square. Okay, this is not p, this is q. 49q square. Okay, we are done with the last two terms. Now this output needs to be multiplied by 36p square plus 49q square. 49q square. When these two equations are again multiplied, I would be employing the same formula of a plus b into a minus b. Here is the term of plus and here is the term of minus. So 36 square would come out as 216 multiplied by 6, which is equal to 1896, if I'm not wrong. No, 1296. Okay, 1296. And the cube or the power of 4 for 7, or simply 49 square. 49 square would come as 2401. Okay, so my answer would come out as 1296 p raised to the power 4 minus 2401 q raised to the power 4. This would be my final output. Okay, this would be my final output. Now we again have a very similar question. The identity we'd be using over here is, I'll be taking you back to the identities. Okay, the identity we would be using over here is this long identity. Okay, and it has been expanded in this form. It has been expanded in this form. Please just reiterate, just relearn and revise this identity. A plus b whole cube is equal to a cube plus b cube plus 3a square b plus 3ab square. Okay, similarly a minus b whole cube is equal to a cube minus b cube minus 3a square b plus 3ab square. Yep, coming back to the question, 62 is equal to a, 22 is equal to b. So I have the expression as a cube minus 3 a square b plus 3ab square minus b cube whole upon 8 into 8 into 8. Okay, so if I try to compress this opened up identity down, I can write it as a minus b whole cube. Okay, so a is 62, b is 22, so 62 minus 22 whole cube divided by 8 cube, this would come out as 40 cube divided by 8 cube, and this would come out as 8 fives are 40, so 5 cube would be the answer, and the value of 5 cube is nothing but 125. So this is my final answer. Okay, so this is how algebra helps you out in tough situations, where if you would sit down and solve it, it'll take you an entire examination to solve this question. But we already have the algebraic identities with us, so it gets solved in seconds. Now there is a question of surds and indices. What we'll be doing is, we'll be expanding the term whatever is given to us. It says 1 plus x whole cube. I'll be simply expanding it down because there is no multiplication, so I won't be afraid of it. 1 plus x whole cube. 1 plus x cube plus 3a square b plus 3ab square plus a cube minus b cube minus 3a square b plus 3ab square. This is the second bracket, and then there is a minus 8 over here. Okay, because minus 2 when cubed down would give me minus 8. Let me see the terms which would cancel themselves out. There is a plus 3x and there is a minus 3x. There is a plus, no, this is fine. This is also fine. There is an x cube and this would also go away. There is, no, I don't think there's anything else. Then we have 2 plus 6x square minus 8, or I can simply write it down as 6 square minus 6. I can also write it down as 6 common x square minus 1. So 6 multiplied by x square minus 1, and this would be my correct answer, because if I take the minus sign inside, it would turn itself down to 1 minus x square. From 1 minus x square, it will turn itself down to x square minus 1 multiplied by 6. So I hope it clears the air of whatever is going on through this identity. Okay, moving ahead, we have the strongest concepts of surds and indices. I would be helping you with surds and indices, and the surds and indices concept starts like this. Let's assume there is a number a and it is raised to the power n, and then it is multiplied by b, which is also raised to the power n. So once that happens, I can conclude that you can multiply a and b together first and then put a power of n on them. Okay, then you can put the power of n on them. So this is the first identity of surds. Okay, this is the first identity of surds. Further, let's assume that a raised to the power n is multiplied by a raised to the power m. So a can be written as m plus n. When we speak out the identity, we say that the bases are same, so the powers would be added in multiplication. Similarly, if the bases are same and there is a division sign between a raised to the power n and a raised to the power m, the powers would get subtracted. Okay, n minus m. Remember this, the one which stays on top is a positive power, the one which stays on the bottom is a negative power. Similarly, when there is a root situation, let's assume this is a square root situation, then we can say that a raised to the power half is equal to root a. Okay, a raised to the power half is root a. Similarly, when there is a situation of cube root of a, that would give me a raised to the power 1 by 3. Similarly, if there is a root of the order n and that is applied on a, I can say that a raised to the power 1 by n is my output. Okay, a raised to the power 1 by n is my output. There can be a situation when a raised to the power m is again raised to another power of n. So in that case, the powers would be multiplied, m multiplied by n, because a raised to the power m would be happening n times. Okay, a raised to the power meta would be happening neta times. Okay, m multiplied by n. So that is one of the other expressions which are important. Again, the very standard formats would be a raised to the power 0 is nothing but 1, but a raised to the power 1 would give it itself its own identity, which is equal to a. Okay, which would give it its own identity, which is equal to a. There is a converse identity which says that when a raised to the power x is equal to a raised to the power y, that means that both the powers are equal. Okay, this means that both the powers are equal. I have to refer to the sheets because these things are very implicit for anybody who teaches, but when I have to teach it out, I shouldn't skip anything which is important to you. Okay, so that's why, and that's when I have to talk like that. Similarly, whenever I've talked in this identity, when anything goes in the denominator, the power changes to a negative sign. So whenever I talk about a raised to power n and it is in the denominator, it would come out and come back as a raised to the power minus n. Okay, a raised to the power minus n. Anything in the denominator, if you need to bring it back to the numerator, there is supposed to be a minus sign. I don't think there's anything else left. There is one very particular identity which I would like you to know. A to the power p, when root down to this, it can be written as a upon b whole raised to the power 1 upon n. Okay, this is 1 upon n. I think I've covered everything over here. Okay, so we'll be moving on to the questions that we have. See the standard form where we are coming from. 2 by 3, 2 by 3 is a common base. When the bases are common and the equation is supposed to be equal, then all the powers are equal. Okay, all the operations inside the powers are supposed to be equal. Now see this. Yeah, 3, this entire equation is going to be in the multiplication form. Similarly, this entire equation is going to be in the multiplication form. 3 multiplied by 2x plus 3 multiplied by minus 3 by 4 is equal to 2 by 3 multiplied by 3x plus 7 multiplied by minus 6 by 5. Okay, shall we start cutting them off right away? No, I don't think that would be a good idea. Okay, so let us start by cutting off at least the minus signs. Okay, so this is where we start off from. The minus signs can be cut out. 3 3s are 9. 9 by 4 multiplied by 2x plus 3. The left hand side is complete. Going to the right hand side, it is 12 by 15, right? Multiplied by 3x plus 7. 3 4s are 12, 3 5s are 15. Mm, there's nothing more that can be done. Okay. 45 is equal to 16. 45 would be multiplied by 2x plus 3, and 16 would be multiplied by 3x plus 7. So 45 twos are 90x plus 135 would be equal to 48x plus 112. This would bring me to 42x on the left hand side, 42x on the left hand side, and this would be equal to 23, if I'm not wrong. Yeah, 23. So the value of 42x is equal to 23. In the equation itself, it is asking me 2 minus 42x when kept in root. What is the answer? If the value of 42x is equal to 23, I'll simply plug in the value of 23 over here. And this is not plus 23, this is a minus 23. So when a minus 23 is plugged in a minus 42, the answer comes out to be plus 23. Plus 23, and there is this sign of a root. This root means a square root, and the square root means 25. The root of 25 is nothing but 5. So this is my outcome. This is my final answer. All the steps and all the equations of surds and indices was completed over here in the same question. Okay. Moving to this question, it is asking me to pull them out into their prime factors, and then it's asking me for an operation on the prime factors. Okay. So what I would do is I would put them out in their prime factors as soon as possible. This is 2357. I would recommend you to do the same thing in the exam. We are starting with 56. These are going to be the powers which I'll be writing down. 7 8s are 56. 1 power of 7 and 3 powers of 2. 7 8s are 56. 75, 25 times 3. So 1 power of 3 and 2 powers of 5. Talking about 60, 12 5s are 60, or 15 4s are 60. Is there a better way out? 6 into 10 is also 60. I'll just quickly write it down. 6 into 10 is 60. So there is a 2, there is a 5, there is a 3, and there is a 2. So 2 powers of 2, 2 powers of 2 for 60, 1 power of 3, and 1 power of 5. Okay, we have 60. Then we'll be talking about 84. 84 is 7 into 12. So 7 into 4 into 3, 2 powers of 2. We're talking about 84 over here. 2 powers of 2, 1 power of 3, and 1 power of 7. This is 84. Coming down to 210. 210 is 7 into 30. 1 power of 5 and 1 power of 3 and 1 power of 2. So it has all 1, 2, 3, and 4. It has all the powers. We're talking about 210. 1, 1, 1, and 1. Okay. I'll be adding all of them up. So the value of P would come down to 3, and this would come down to 8. The value of 3, or the value of Q, would be equal to 4. The value of 5 would be equal to, the value of R would be equal to 4, and the value of S would be equal to 3. So we have PQ and R, PQRS with us. The operation that needs to be applied is P plus Q whole upon S plus R. Okay. So P plus Q is 12. 12 upon S is equal to 3 plus R is equal to 4. 3 4s are 12, and my final answer would be 8. Okay. So this is what we have to do. We have to split them down into their own prime factors, use their powers, and then apply a small operation on them. Okay. Apply a small operation on them. Pretty easy, doable, very much doable. Okay, do let me know if there's any doubt. Now, again, a question of indices. We have three similar terms. We'll be taking one of them out as common, 3 raised to power 33, and there is whatever is left is common is 1 plus 1 plus 1. Whatever left common is 1 plus 1 plus 1. Then again, 2 raised to power 33 is taken out as common, and 1 plus 1 is left behind. Okay, so 3 raised to power 33 multiplied by 3 multiplied by 2 raised to power 33 multiplied by 2. 3 raised to power 33 is nothing but 34. 3 raised to power 34, and 2 raised to power 34 multiplied by 2 is nothing but 2 raised to power 34. When the powers are same and the bases are available, so the bases can be multiplied. Their original theme, the original operation which is between them, can be carried out. So this is nothing but 6 raised to power 34, and this is also equal to 6 raised to the power x. So the value of 34 is equal to x. Okay, x is equal to 34, and this is my final answer. Moving ahead, it talks about 21 raised to the power something, let's assume y, plus 20 20 raised to the power y again is equal to 29 raised to the power y again. Okay, so the students who are a little familiar and a little old for this exam, little old, what I mean, little experience with this examination, this is a standard triplet. Okay, this is a standard triplet. You can form a triangle with it using the Pythagoras theorem, and the triangle would be having sides 21, 20, and 29. Okay, so when we apply this rule to a triangle and we use the Pythagoras theorem, the rule comes out to be 21 square plus 20 square is equal to 29 square. This theorem is called the Pythagoras theorem, and 21 raised to power 2, 20 raised to power 2 is equal to 29 raised to power 2. So the value of root x is nothing but 2, and I'll have to square them both sides to remove the root from the equation. So the value of x would come down to 4. So 4 is my answer, and A is the option that we're looking for. Moving ahead, which of the following numbers will completely divide 6 raised to power 61, 6 raised to power 62, plus 6 raised to power 63, plus 6 raised to power 64? So the smallest number can be taken out common, and rest of them can be left behind. 6 raised to power 61 is taken out as common, so we'll be left with 1 in the first place, 6 raised to the power 1 in the second place, 6 raised to the power 2 in the third place, and 6 raised to the power 3 in the fourth place. Now this is 1 plus 6 plus 36 plus 216. 6 raised to the power 61, and this entire equation is in our hands. 1 plus 6 plus 36 plus 216. 6 plus 6 plus 6 is 18, and there is 1 19. 1 2 2 plus 3 5, and that's 5. 5, then another 2. 259 is my supposed answer. 36 plus 6 is 42. 52. 52 plus 7, 59. Yep, this is good. So we have 259 multiplied by 6 raised to power 51. Now I need to see if it is it's possible with 13, 7, or 11. This is not possible with 11. With 7, 7, yep. This is definitely divisible by 7. When 7 is multiplied by 7 3s are 21 and 7 7s are 49. So it's 7 into 37. So 7 is what it is completely divisible of. Okay. The only trick was to take the smallest number out as common. Okay. Now moving on. There is a concept of AP which I would be teaching over here. Now we'd be talking about AP, and AP stands for arithmetic progression. Arithmetic progression. There is another progression which you might know about, which is called GP, and it is called geometric progression. So what happens in an arithmetic progression is that let's say the first term is a. Similarly, the first term is a in geometric progression. In arithmetic progression, let the first term be a, then there is something called d. D is basically called the common difference. So what happens in an arithmetic progression is that when the first term is a, the second term is going to be a plus d. Okay, the second term is going to be a plus d. The third term is going to be a plus 2d. The fourth term is going to be a plus 3d, and so on. Okay. Similarly, in a geometric progression, what happens is the first term is a. The common difference between the two terms is nothing but r. So the second term is going to be AR. The third term is going to be AR square, and the third term is going to be AR cube. The fourth term, the fifth term would be AR4, and so on. So what's happening in an AP is that in two terms, in between two terms, let's talk about 1, 5, 9, 13, 17, 21, 25, and 29. Okay, so there is a common gap of 4 between each term. There is a common gap of 4 between each term. The series is progressing with a factor of 4 in it. Okay, with a factor of 4 in it. Similarly, when I talk about a GP, let's assume the first term is 1 and I'm multiplying the very next term with 2. So 2, then 4, then 8, then 16, then 32, then 64, then 128, and so on. If you wish to find out the common difference in an AP, you have to see the difference between any two consecutive terms. Okay, you have to see the difference between any two consecutive terms, which means that A2 minus A1, the second term minus the first term, will give you the difference between them. Similarly, in a GP, if you wish to see what is the R, the common factor, okay, or what is the thing, the common difference between two terms in a GP, that can be done with the help of A2 upon A1. A2 by A1, what do I mean by that is that the second term can be divided by the first term, which would ultimately give me the output, which is AR upon A, which is also equal to R. And that's what I'm talking about. In geometric progressions, the progression takes place in terms of multiples. Okay, it takes place in terms of multiples. In terms of arithmetic progression, the progression takes place in sum or minus as well. Okay, this entire equation of arithmetic progression can go in a negative direction as well when the common difference between the two terms is in a negative mode. Okay, and in a geometric progression, the difference between the two terms or the series can dwindle down to a lower and a lower number when the common difference is less than 1. Okay, when r is less than 1. In the next page here on the right hand side, I'll talk about the nth term, of both AP and GP. When I say nth term, nth terms means any term. Okay, nth terms means any term which you pick. Nth term means any term which you pick. So if I wish to pick a term, let's say an. So if I need to locate the nth term, what would happen is an is equal to a plus n minus 1 multiplied by d. A, as a standard definition, is the first term in the sequence. N is the number of terms or the nth term we are talking about. Let's say we have to find out the 15th term of a series. So n in this equation would come out to be 15. Okay, it's basically the number of term which we're talking about. Let's talk about d. D is the common difference. Common difference in the previous question, coming back here, the common difference in the previous question was equal to 4. Okay, the d is equal to 4. Common difference is 4. All these are common differences, and here r is equal to 2. Again, r is equal to 2. R is another common factor. Okay, the common factor by which the every next term is multiplied. So for an AP, if you wish to find the nth term, so this is the formula. Similarly, for a GP, if you wish to find out the nth term, for that an is equal to a into r raised to the power n minus 1. A being again the first term, r being common difference the common difference or the common factor, okay, between the two terms, what, or the factor which will be multiplied in every consecutive term, that is equal to r. Instead of calling it common difference, it can also be called the standard definition says that this is called the common ratio, okay, the common ratio r. And again, n stands for the nth term that we are talking about. Let me take you back. This question we were dealing with in the last slide. Let's say we need to find out the first, second, third, fourth, and fifth. I need to find out the fifth term of this series. So, to find out the fifth term of the series, I should know the first term, I should know the common ratio, I should know n, and I should know this minus 1 technique. A over here is 1, that is where we begin at, the first term, multiplied by r. We've already calculated r as equal to 2. Okay, I'm going to replace it by 2 later. Just give me a second. Yeah, this is r which is equal to 2 n raised to the power n minus 1. We're talking about the fifth term over here. So n minus 1 would be 5 minus 1 or simply 4. When I do this, 1 multiplied by 2 raised to the power 4, 2 raised to the power is 2 4s are 8, 2 2s are 4, 4 2s are 8, 8 2s are 16. So the fourth power of 2 is equal to 16, and that is my fifth term of this geometric progression. Okay, so here I lay down the foundation of geometric progression nth term. Similarly, this is the standard formula for finding out the nth term of an AP. Okay, this is the standard formula of finding out the nth term of an AP. Everything has been explained on the previous slide, and we are explaining better things and the nth term sequence in the next slide. Now, there is a very standard formula which would be followed for finding out the sum of AP. Finding out the sum of AP. The sum of AP means if I wanted to add up all these terms, I need to add up 1, 5, 9, 13, 17, 21, 25, and 29. So there is a small formula for it. You can always calculate them, you can always add them up, but let's assume the addition is pretty huge. So it's going to be a problem. So it's best to have a standard formula for it. So the sum of AP formula stands for Sn. Sn is equal to sum of n terms, which is equal to n by 2, n being the number of terms, in the bracket 2a plus n minus 1 multiplied by d. All the terms which were explained in the nth term formula, the terms are the same. So I won't be explaining them again. The only second formula which I have on my mind is Sn is equal to n by 2 multiplied by a plus l, and l stands here for the last term. Okay, so this is a formula which you must catch hold of. The formula on the right hand side is not more important than the one on the left hand side, but I would still ask you to memorize it. Okay, still ask you to memorize it. It's nothing but we've replaced the an, and an may be called the last term, and we've put it over here in the formula. So this is not something which is coming out of the blue. Okay, there is one more small formula which I'll be introducing here in concept number 12. Okay, let me introduce that to you because I've already talked about GP. When we talk about GP, we've already discussed the sum of GP. Sorry, the terms of GP. Okay, we've discussed the nth term of GP already. I'll be reintroducing the same over here. The nth term of a GP, which is, let's say, an, is equal to small a, that is the first term, multiplied by r, which is the common ratio, to the power n minus 1. Sorry, okay. So we have this established that if we wish to reach any term of the GP, this is how I will take it forward. Now, coming to coming down to the next point, which is the sum of GP. Okay, the sum of GP. The sum of GP is a very interesting concept. What happens is that whenever there are terms in a GP, there is a formula that can be employed to find out the sum of GP. The sum of GP is equal to A multiplied by r raised to the power n minus 1 whole upon r minus 1. Okay, so this is the standard formula for the sum of GP. R stands for the common ratio, A stands for the first term. Also, whenever the ratio R is greater than 1, this formula holds true. As soon as the value of R goes down, like goes below 1, the formula changes itself. The formula comes out to be R raised to the power A multiplied by 1 minus R raised to the power n whole upon 1 minus R. Okay. The formula changing for r less than 1 seems to be very, very valid for a very strong reason. And that very strong reason is that as soon as the value of r remains more than 1, the entire sum comes out to be positive. And as soon as the value of r goes less than 1, if we employ the same formula, our output would come out as a negative value. And we don't want the sum to be a negative value. So it's important to have a different formula, and there is nothing. It's a simple tweaking of the formula. Okay, it's a simple tweaking of the same formula. So you must remember both the formulas. And this sum of GP is meant for finite terms. Okay, it's meant for finite terms. There is a possibility that in the examination it might ask you for sum of GP for infinite terms. Okay, for infinite terms, the sum of GP is a divided by 1 minus r, or a divided by 1 minus, or r minus 1, r minus 1. Okay, so these are the two, or these are the three formulas which you must remember. I hope I've made myself very clear. Now we'll be solving two questions on AP, and we'll be solving two questions on GP. Okay, so the first question on AP is this. I'll be solving this entire question here on the left hand side. We are lucky to have all the formulas here on the right hand side. Find the nth term of the AP. The AP goes like this: 1, 4, 7, 10, and so on. If the number of terms are 15. 15. Okay, so there are 15 terms, and it is asking me to find the nth term. It means it is asking me to find the last term. Okay, it is asking me to find the last term. If the last term is the 15th term, I would employ that in my formula. The formula here says that A15 is equal to A plus 15 minus 1 multiplied by the common difference, that is D. Okay, the common difference over here, as we can see, is 3. Let us verify it one more time. 7 minus 4 is again 3, and 10 minus 7 is again 3. So we can conclude easily that the common difference is nothing but 3. Let's use A as well. A being the first term of the AP is 1. 1 plus 15 minus 1 is 14. 14 multiplied by 3 is 42. So 42 plus 1 is 43. So 43 is my A15, or my 15th term. Okay, moving on. Sum of the AP series 1, 2, 3, 4. This is going on till 15. Okay, I'll be telling you multiple formulas over here, but let's learn the standard formula first. The sum of the AP, which has n terms, is equal to n by 2 multiplied by 2a plus n minus 1 multiplied by the common difference. Okay, or n by 2 multiplied by the first term plus the last term. As we are well aware that the first term is 1 and the last term is 15, and also there are 15 terms in the AP. 15 upon 2 multiplied by 15 plus 1. So this is 2. 16 upon 2 is 8. 8 into 15 is 120. So 120 is my sum using the shorter formula. Further, if I use the long formula again, 15 is the number of terms, 15 upon 2 multiplied 2a is 2 times of 1, that is 2, plus n being 15. 15 minus 1 is 14. 14 minus the common difference. The common difference in the consecutive terms is 1. Common difference in the consecutive terms is 1. So d is equal to 1. This is 14 ones are, and plus this is 16. 16 by 2 is again 8. So 15 into 8 would again give me 120. Okay. So the answers on through both the formulas have come out to be the same. Whenever we find the terms in the series 1, 2, 3, and so on till n, then the sum of such a term of such a series is called n into n plus 1, n into n plus 1 divided by 2. If this series converts itself, if this series converts itself into a series which is 1 square and 2 square and 3 square, and it goes on to a point where it becomes n square, the final answer would come out as n into n plus 1 into 2n plus 1 whole divided by 6. Okay, n into n plus 1 into 2n plus 1 whole divided by 6. This is a standard formula which you must learn. Further, 1 cube, 2 cube, 3 cube, and so on till n cube. This comes out to be, this comes out to be n into n plus 1 whole upon 2, and this entire thing is squared. Okay, so this is the standard format which you must learn. We've already talked about this, and applying the same series of 15 over here, 15 multiplied by 15 plus 1 whole upon 2 would again give me the same answer of 120. Okay, so I've shown you 3 different ways to solve the same question. So this is the entire summary of APs. Okay, moving on to GP, we've talked about GP over here, right? If the first term of the GP is 10 and the common ratio is 3, then write the first 5 terms of the GP. I'll be first introducing you to the common way of writing GPs. A into A multiplied by R into AR square into AR cube and AR raised to the power 4. These are the first 5 terms of the GP. Okay, this being the first, second, third, fourth, and fifth term of the GP. So the first term is 10, simple. The second term is 10 into 3, that is 30. The third term has to be multiplied by 3 again, so that means 90. Another 3 into this is 270. Another 3 into this is 810. So this is what solves our question. Moving on. Find the sum of the GP 10, 30, 90, 270, and 810. Firstly, I need to find out A. A is 10. Secondly, I need to find out R. To find out R, I'll use any two consecutive terms, would keep the term which is farther upon the term which is nearer. So the farther term is 30. Farther means the one which is away from us. And nearer is 10. So 30 upon 10. This would give me the value of common ratio as 3. Similarly, let me do it by 90 by 30 just to double check if I'm going in the right direction. Okay, so I have found out my value for r, which is 3. 10 r, we have everything in place. I need to find out the sum of the GP. There are 1 2 3 4 5 terms in the GP. So the sum of the 5 terms of the GP would be a means 10 multiplied by r raised to the power n. R raised to the power n means 3 raised to the power 5 minus 1 whole upon r minus 1. The value of r is 3 minus 1, this is 2. So 10 upon 2 multiplied by 3 raised to the power 5 minus 1. Okay, so this is 2 5 is a 10. 3 raised to the power 5. 3 3 is a 9. 9 9 is a 81. So at 81 we are at 3 raised to the power 4. And then another 3 when multiplied gives me 243. 243 minus 1 multiplied by 5. This is 242. 242 into 5. It would give me 1210. 1210. This is my final answer. Okay. How did I achieve 1210? Let me just show you a quicker method. This is 240 multiplied by 5 plus 2 into 5. When 24 is multiplied by 5, I get a value of 120. There is another 0, so it becomes 1200. Then 5 into 2 is 10, so that is 1210. 1210 is my final answer. We are lucky to have a smaller series over here and a smaller question over here. Had this question been a little long, our formula would have worked very well, and our formula would have given the most accurate answer. But just because this question is short, let me do the manual calculations for you. These two become 300, then this becomes 400. 400 plus 810 becomes 1210. You could have simply added all this up. Okay, not a big deal. Not a big deal at all. So, for those who haven't been able to understand AP and GP, give me a moment and I will run you through the same within a jiffy. I've changed the pen color. Yeah. So for AP, AN, this is what we're talking about, the nth term, that's equal to A plus N minus 1 into D, where A is the first term, N is the nth term we're talking about, D is the common difference. For GP, the nth term stands for A multiplied by R raised to the power N minus 1, where R is the common ratio. For the sum of the AP, Sn is equal to n by 2 multiplied by 2a plus n minus 1 into d, or n by 2 multiplied by a plus l, l being the last term, d being the common difference, a again being the first term, and n being the nth term. For GP, the sum of GP can be written in three ways. If it is a finite GP, then we will have a multiplied by r raised to the power n minus 1 whole upon r minus 1 when r is greater than 1. Just to avoid a negative signature, we flip the use of r whenever the value of the common ratio is less than 1, or the series is dwindling down. That is only when the value of r is less than 1. Then in an infinite series, an infinite loop, or an infinite GP, a upon r minus 1 or a upon 1 minus r. Okay, this is the standard formula for the sum of GP. I hope we are clear with this. Now we'll be moving to complex like concept 13 and concept 14. I would be telling you a few formulas later, but what we can do right now is we can solve this question together. Okay, 1 minus 1 by 2, we're just going to solve this question. Everything is in multiplication. 1 minus 1 by 2 is 1 by 2. 1 minus 1 by 3 is nothing but 2 by 3. 1 minus 1 by 4 is nothing but 3 by 4. So we can see that there is a continued pattern over here, and in the end what I can find is there is 22 upon 23. If I start cancelling out things, I see that the first denominator, starting from the first denominator till the last numerator, everything is gonna get cancelled. So what I would be left with is 1 upon 23, which is my final answer. Okay, I'm telling you the questions first so that you are not swayed by this image in your mind that we always have to apply a formula. If you start solving the question as well, you might be able to reach a conclusion. So I'm just introducing a little flexibility element in your mind by solving the question directly without telling you any formulas. Okay, moving to the next question. Simple roots question. Okay, So root 36 is nothing but 6. We have 6 here. Now talking about 56, 256. 256, the whole thing, root 256 is nothing but the square root, root 256 is nothing but the the square of 16. So we get 16 out of it. Now we get another square which is 1, 2, 9 and 6. Okay, we have 1, 2, 9, 6. Now some people might find it a little difficult to find out the square root of 1, 2, 9 and 6. Okay, so if I use the longer way, let's say 40, 40 would give me 1600. What about 30? 30 would give me 900. So it might be 30 4 or 36. If I go for 34, this would give me 4 4s are 16, 3 3s are 9, 3 4s are 12, 12 2s are 24. This would give me 6 5 1 1 5 6. If I go for 36 square, it would give me 36 on the right, 9 over here, 3 6 are 18, 18 2s are 36. It would give me 1296. So we have the square root of 1296 being equal to 36. Now let me add that to 540. 540 plus 36 gives me 576. The square root of 576 is nothing but 24. Now I have 24 over here and I have 4600 to add with it. At 4600, I would reach 46. At 4600, I would reach 4624 and I need to find out the square root of that. Okay, 4624. Let me take it this way. 50 is 2500, 80 is 6400, 70 is 4900, 60 is 3600. Okay, so if I go for 70, 70 is 4900, which is pretty close to it. So anything between 60 and 70 would do the thing. If I go for 65 square, 6 sevens are 42, that is equal to 4225. Okay, so we are very close to this. It's going to be above 65 for sure. 65, above 65, anything which leaves a last unit digit as 4. So that happens only in the case of 2 and 8. Only in the case of 2 and 8. This means that the answer for this particular question is going to be 68. Okay, because the square of 68 is equal to 4624. Let me prove it to you. Okay, when 68 has to be squared, I would use the last digit, I would square it, I would use the first digit, juxtapose it right next to it, 3664. Then 6 8s are 48, 48 into 2 is 48 into 2 is 96, 96 into 0 is 960, 96 into 10 is 960. This would come as this would come as this would come as 16. 4624 is my final answer. Okay, so we were correct. This question could only and only be solved if you knew how to do square roots pretty quickly, if you remembered most of the square roots or most of the squares of the standard numbers. Even if you don't know, go by my way, the way I taught you. Like we are sitting somewhere at 4600. So any number you may start by 40. 40 square is 1600. We are very far. Let's do 60 square. 60 square is 3600. We are getting closer. What if we do 70 square? 70 square is 4900. So 4900 is pretty close to 4600. So we just need to come a little lesser than 70 and not very close to 60. So we need to find out we need to check the last digit. The last digit is 4, which can be created by squaring either 2 or squaring either 8. If we do a square of 2, that will lead us only to 62 square. If we do a square of 8, it will lead us only to 68 square. 62 square is not in our favor, but 68 square might be in our favor because our answer is very close to 70 square. Okay, so I hope you understood what I have taught you, and if there's any problem, do write about it in the comment box. Now we will have to employ some or the other formulas for this. So give me a moment, I will come back with the formulas. See, we've already solved this question in which all the standard identities have been, the standard forms of squares and square roots have been used. So there are questions like these which need very specialized and simple formulas to learn, and you have to learn the formulas and apply them straight away. Okay. Similarly for this, actually in this particular series, if you see 1 by 3, all the common differences are the same. The common ratios between the two terms is, the difference between the size of the two terms is 4. So we have a standard formula for it as well. We've discussed it in the beginning. Same for this, there is a good standard formula. And this question is a special question. I'll put a star mark over here, and you'll very soon know why it is so special. Then we will have the concept of rationalization, which I would introduce to you, and then a few numbers, how to compare the numbers which are in the roots. I'll help you with that. And then we have simple concepts of componendos and dividendos. Okay. So let me first take you to concept number 13, in which we've already attempted two questions. Sorry, we've already attempted two questions and we haven't introduced a single formula for it. So, firstly, I would introduce the concept of rationalization. Rationalization, and this usually happens of the denominator. When I say rationalization of the denominator, it usually happens as soon as there is a term which contains roots, which is there in the denominator. Okay. In any denominator, if you ever encounter roots, that is the time when you have to use this concept of rationalizing the denominator. Our main focus is to remove the roots from the denominator. So what we do is we multiply the same, we multiply the fraction by its conjugate. Okay. When I say conjugate, it basically means this, we'll use the same terms, but we will have a different sign over here. And there is a very logical explanation for that. The logical explanation says when a plus b is multiplied by b plus, when a plus b is multiplied by b minus a, the output what we get is b square minus a square. And now this b square minus a square is very useful to us because the squaring of these numbers would lead to the flying away of the roof or the roots. The roots will fly away, the roots will vanish as soon as we get this identity into play. So what we do is the conjugate of a plus b, of root a plus root b, is nothing but a root a minus root b. So what we do is whenever we encounter a place where 1 upon root a plus root b is given, we need to rationalize the denominator. We multiply both the sides, the bottom, like when I say the bottom, I mean the numerator, the denominator as well as the numerator with its conjugate. Okay. So root a minus root b multiplied by, then again root a minus root b. This entire thing is multiplied to the first equation, root a plus root b. So these two things, the denominator gets together and it creates a situation like this. Root a minus root b would stay in the numerator and a minus b would be my output. When root a minus root b multiplied by root a plus root b is there, then root a whole square minus root b whole square comes out, which is nothing but a minus b in this equation. A minus b in this equation. I hope you understand where I'm coming from. Okay, so this is known as rationalization of the denominator. It is seldom used in the examination, but yeah, you must know whenever you encounter roots in the denominator, there shouldn't be any roots in the denominator. You should always shift them to the numerator side. Then coming down to a few standard formulas. The few standard formulas are whenever you encounter a root of a, then another root within it, then another root of a within it, another root of a, and so on till infinity. And you're asked what is the value of this question. So you would answer that the value of this question is nothing but a. Okay, you get it? Whenever continuous roots are there of the same number, the answer is the same number. Secondly, there is a finite series of the same question. there is a root of a, then another small root of a, then another small root of a, then another small root of a, and so on till n times. So whenever this sort of a question comes up, your answer would be a to the root, to the power. Okay, this everything is in the power size, and it is 2 raised to the power n minus 1 whole raised to the power 2 n. Okay, 2 raised to the power n minus 1 upon 2 raised to the power n. That would be my final output, and you need to memorize these techniques. Let's assume there is a cube root. There is a cube root of a, then another cube root of a, then another cube root of a, and so on till infinity. So the answer of this would be the square root of a. What we're essentially doing is, if we have a cube root of a, it would shift to square root of a. Okay, it would shift to square root of a. So this is the most essential part of it. I'll be generalizing the formula. The generalization of the formula is, whenever we have the nth root of a in a series, whenever I have the nth root of a in a series and it goes till infinity, then a would assume a root upon itself of the order of n minus 1. Okay, it would take, it would assume root of a to the order of n minus 1. Got it? Got it? Similarly, this operation, this entire operation is for multiplication. Okay, this entire operation is for multiplication. I'll be moving forward to the next page. I'll be moving forward to the next page. If there is an operation of division, okay, there is an operation of division of the order, let's say an, then another division a to the nth power, another division sign to the nth power, another division to the nth power of a. The output would be a raised to the power n minus a raised to the power n plus 1, and it would be a division. Okay, 1 upon n plus 1, which is equal to the n plus 1th power, the n plus 1th root of a. Okay, this is a very standard formula. You might not see this particular one much in the examination, but it definitely exists. Then if a is multiplied, if a is multiplied a times, multiple times, okay, let's say n times, so a assumes the power of n. Then further taking it to a point that a plus a plus a plus a going on in roots. This goes on in roots till infinity. The value is x plus 1. Okay, the value if in is x plus 1 when a can be factorized into two numbers which are consecutive in nature. Okay, let's say if we assume that a is equal to 6, so 2 into 3 becomes 6, and we get it with the value of plus in the denominator of plus in the roots, then my answer would be 3. Similarly, if I get the same question with roots and a negative sign, with roots and a negative sign till infinity, my value comes out to be x. My value would come out to be, would come out to 2, particularly in this question. Okay, and there is one last factor which I would like to tell you about. If a cannot be factorized into these two consecutives of it being x and x plus 1, there is a standard formula which can be used, which is 1 plus 4a plus minus 1 depending on the question whole upon 2. Okay, this needs to be solved first, and then this needs to be solved when there is a consecutive whenever we find a, but it cannot be split into consecutive factors. Okay, I hope we are pretty much done with this, and there's not much to think about. Yep. So, going to this question. Now we have this root 3 times. Therefore, n is equal to 3. And we just learned the formula a raised to the power 2n minus 1 whole upon 2n in such cases. So 5 raised to the power 2 cube minus 1 whole upon 2 cube. So 5 raised to the power 7, because 2 cube is 8, 7 by 8. This is my final outcome. Okay. Okay, I hope I've made myself very clear with this example. Moving to the next question. Now, in this series, I have taught you this already. Let me take you to the point where I have taught you the same. Even if we don't find it, we would, like, I will be teaching it back to you. Just a second. It all seems so colorful. I have taught you this somewhere, but no problem. No problem. I will bring you to the same level again. Need not worry about it. AP, GP, and this series. Now you see that the difference between the two consecutive terms is 4. Okay, so the formula is 1 upon difference 1 upon first term minus 1 upon last term. This is the formula whenever there is a sum of this series. 1 upon difference is 1 upon 4. The first term would be 1 by 3. The last term would be 1 by 903. This is 1 by 4 into 900 upon 903 into 3. Okay, so 3 ones are 3, and then 300. This is 100. This is 301, and this 4. This is 25. So the value of this series is nothing but 25 upon 301. This is the standard formula which you need to remember for all such questions where you see a consecutive series which has a gap of 4 between the two consecutive digits. Okay, now talking about this, we again have consecutive digits. The gap is standard, the gap is uniform, which is 1. Similarly, in the next series, the gap is again uniform, which is equal to 1. So I'll find out the value of x. The value of x would be 1 upon difference, which is 1 upon the difference, 1 upon 1. In the first term is 1 by 12. In the last term is 1 upon 24. Similarly, I'll find out the value of y. The value of y is, I'll find out the value for y. The value for y would come out as 1 upon the difference, which is 1. Then the first term is 1 by 36. I've already taught, that's why I'm moving a little fast. Okay, and 1 by 36 minus 1 by 72. 24 minus 12 is 12. 12 upon 24 is half. So the value of x is nothing but half, right? 24 minus 12 by 24, it's basically 1 minus half. So 1 minus half is nothing but half. So we have its value over here. Similarly, 1 by 12, just a second, let me check. 1 by 36, 1 by 72. I think we are good to go. I think we are. There's a small error that I am committing over here, and it completely got overlooked. See, whenever I do 1 by 12 minus 1 by 24, 1 by 12 is basically made up out of two 1 by 24. So my answer would be 1 by 24. Okay, the simple subtraction. y again 1 by 36 minus 1 by 72, it would give me the answer as 1 by 72. This is the value of x and this is the value of y. So whenever I talk about x upon y, the value of x is 1 by 24 and the value of y is 1 by 72. Okay, so 24 ones are 24 and 24 threes are 72. So my answer is 3 for this particular question. Moving to the next question. If you see very closely, we have two squares over here, one of them being 1 upon 2 square and the other one being 3 square. The difference between 2 square, which is equal to 4, and the difference between 3 square, which is equal to 9, is equal to 5. So what I'm able to see over here is that this is a combination of 1 by 4 minus 1 by 9. I'll break it down for you. 1 by 4 minus 1 by 9 is equal to 9 minus 4 upon 4 into 9, which is equal to 5 by 4 into 9. And this 5 by 4 into 9 has been represented in such a beautiful manner that you would be flabbergasted to see whatever is going on here. Okay, you will be shocked. You'll be shocked to see that how well this question has been made. I'll just write it more clearly. This is 2 raised to the power 2 multiplied by 3 raised to the power 2. See how simple a term of 1 by 4 and 1 by 9 could be written like this in such a complicated manner. So this means we have to ease down ourselves to this level. Okay. Now as we've eased down, I'll take you to another step. I'm talking about 1 upon 3 raised to the power 2 and 4 raised to the power 2. When 3 raised to the power 2 is opened, it's 9. 4 raised to the power 2 is 16. The gap is that of 7. So I can easily say that 1 by 9 minus 1 by 16 would produce a gap of 7, which is there in the numerator naturally, right? So this 7 upon 3 square into 4 square is evident. It's pretty evident. So instead of writing this tough equation that we've been given in the question, we should rather write the easier equation. And the easier equation is this. So we can easily see a series that is coming up. I'll just do the last sum a little more quickly. 9 square is 81, 10 square is 100, the gap is 19, which is visible in the numerator. So that means we are on track. 1 by 4 minus 1 by 9 plus 1 by 9 minus 1 by 16 plus 1 by 16 minus 1 by 25 plus and so on. This goes to 1 by 81 minus 1 by 100. As simple as that. As we've seen that we are able to figure out consecutive terms being cancelling. We are able to figure out, see, consecutive terms are cancelling themselves. This means everything in the center would vanish away and all I would be left with are the terminal terms. What do the terminal terms say? The terminal terms say that 1 by 4 minus 1 by 100 would be my answer. So 1 by 4 minus 1 by 100 is 100 minus 4 whole upon 100 into 4. This is equal to 96 into 96 upon 400. So 4 ones are, this is 100 and then this is 24. Then 4, what? 4 6 are 24 and 4 25 is 100. So my final answer comes out to be 6 upon 25. That is what we were looking for. Okay. So the only code that you're supposed to crack is pick up one term and try to tinker with it as much as you can, and tinker with it in such a manner that you're able to achieve an easy result for yourself. See how complicated a term 5 upon 2 raised to the power 2 and 3 raised to the power 2 can simply be written as 1 by 4 minus 1 by 9. See, so this comes with experience. Solve as many questions as possible and you'll be able to get through. Now, this is where we use a lot of rationalization and this is very easy to understand. Okay, there is x, the value of x is root 7 plus root 5 whole upon root 7 minus root 5. Then we have y, which is equal to root 7 minus root 5 whole upon root 7 plus root 5. A simple addition needs to take place between the two terms. When we are adding it, we'll have to have LCM of the denominators. The LCM of the denominators is very useful to us. Why? Because it also leads to the rationalization of the denominators. Once we rationalize it, we are able to get a term which is root 7 square, which is 7, minus root 5 square, which is 5. So there is no hassle of rationalizing it anymore. Then we have the square, because this goes and cross multiplies there and this goes and cross multiplies there. So we have root 7 plus root 5 whole square plus root 7 minus root 5 whole square. Whenever we let us solve it completely. Let me not take you to the identities back. Root 7 square is 7 plus 5 plus 2 root 35. There is a plus sign in the middle with 7 plus 5 minus 2 root 35. These two are opposite in nature, so they would get cancelled out. 7 plus 5 is 12. 12 into 2 is 24. 24 upon 7 minus 5 is 2. My final answer comes out to be 12. Okay, so this is how we take things forward. Now, this is a question which has only three terms: 7, 5, and 45. So I will write all of them down. And 7, 45, and 11. Okay, 7, 45, and 11. All of them have the same term attached to it, the same root attached to it. 11 is always seen with the under root of 3. 45 is always seen with an under root of 4. And 7 is always seen with the under root of 2. Okay, this is nothing but the root, okay, the square root. So we have three kinds of roots: the square root, the cube root, and the quad root. Okay, so 2, 3, and 4. I'll have to take the LCM out of it. The LCM of this is the least common multiple, which is equal to 12. As 7 is attached with 2, 45 is attached with 4, and 11 is attached with 3, I will have to bring all of them down to 12. So for 4 to become 12, I will have to cube 45. For 7, for this 2 to become 12, I will have to put the power of 6 against it. For 3 to become 12, I will have to put the power of 4 against it. Okay. So let me try to compare these things all together. If I do a 7 square, I get 49, and the square would help me with the power of 3. So there is a 45 with the power of 3, and there is a 49 with the power of 3. So this definitely means that 7 is greater than 45 in the question. Okay. Now, let me try to figure out if where 11 would lie. Okay. So the value of 11 right now, as I can see, is 11 raised to the power 4. If I do a square of it, if I allow a square of it to be there, or let's say a cube of it, it's 1331 into 11. Let me go a step further. It's 14641. Now there's this cube of 5 or 50 over here. It's very close to 50. So 14641. Then I have a cube of 50 over here. 50 cube means 1, 2, 5, 1, 2, 3. Okay, so this is somewhere in the figures of 1,25,000. This is somewhere in the figures of 14,000 something. And when I talk about 45 cube, it has already been established that it is less than 1,25,000. Okay, so let me see where 45 cube will land me up. It's 9 cube multiplied by 5 cube. 5 cube talks about what? 125. And 9 cube is definitely lesser than 10 cube, which we've already considered over here. 9 cube is much smaller than 10 cube. 9 cube is 81 into 9 is 9 ones are 9. This is 729. So 729 multiplied by 125 is definitely lower than this, but it is much larger as compared to 11 cube. So 7 would be greater than 45, would be greater than 11. So 7, 45, and 11. I find this to be in option number 3, and this is my answer. Okay. The LCM portion is where till where you'll need my help. After that, it's your intelligence where and how you'd like to approach the problem. Okay. Moving ahead, which is larger? In such questions, whenever you find out that the question asks you what is larger, what is not larger, and whatever, I would recommend you as soon as you see the roots, just completely square it off. Okay, square it off. 8 square plus 3 square plus um, 2 into 8 into 3. So this comes out to be 8 plus 3. This is root 8 square is 8 plus root 3 square is 3 plus 2 root 8 into 3. This is the first one. I'm doing nothing, just squaring 6 plus 5 plus 2 root 6 into 5. The sum is equal. 8 plus 3 is 11, 6 plus 5 is 11. But this is nothing but 2 root 24 and this is nothing but 2 root 30. This equation has a higher level in the root. So this means this one is larger. So root 6 plus root 5 is larger of the two. In such questions, you have no outcome other than you don't have any other way to solve it other than solving it by squaring it. Okay, this is the simplest way. If a is greater than b, then a square would also definitely be greater than b square. Okay, you get it? And this is nothing, I'm just having happy fizz. We again have a similar problem. Root 9 and root 7, root 11 and root 9. Okay, so this comes out as 9 plus 7 minus 2 root 63. Then again 11 plus 9 minus 2 root 99. Okay, 9 plus 7 is 16 and 11 plus 9 is 20. Okay, out of 16 we are reducing a lower number which is 2 root 63, and out of 20 we are reducing a bigger number which is 2 root 99. Let me just try to solve it. Root 63 is very close to 8, very close to 8, so 8 16, but a little less than 16. On the other hand, this is 8 and this is going to be 2 into 8, so 16 minus 16, this is somewhat close to 0. On the other hand, 20 minus 2 into root 10, this is again in a position, see, this is not root 10, this is 10. Now we've reached a point sorry, now we've reached a point where both the answers come very close to 0. Okay, both the answers come very close to 0. As we have reached this juncture, there is a small way to crack it. If the product and greatest product of the number will be smallest. Okay, so if the product, let's say, is 9 sevens are 63 over here, and here 11 nines are 99. Wherever the product of these two numbers, wherever the product of these two numbers is 11 minus root 9, wherever the number is greater, okay, wherever the number is greater in the two, that is where the number would be smaller. Okay, so if 99, like we know that 99 is greater than 63, then the value attached to 99 would be lesser. Okay, the value attached to 99 would be lesser. So 11 root 11 minus root 9 is lesser as compared to root 9 minus root 7. Okay, moving ahead. Now I can see that the multiples like 21 into 2 and 6 and root 7. It has been asked which value would be greater. So I am doing 21 plus 2 plus 2 root 42. Then I have 6 plus 7 plus 2 root 42. This 2 root 42 is constant. Out of this, this has a sum of 23 and this has a sum of 13. So naturally, this side is greater. I'm using the same, I'm using the same method of squaring it. Okay. We got stuck in this question. That is why I had to bring in the weapons. The weapon says that whenever, whenever the difference between the two roots which are there in the question is the same, then you'll have to check the multiple. The bigger the multiple, the smaller the number. Okay, so multiple 11 into 9 is 99 and 9 into 7 is 63. So 99 is greater than 63. That means the number associated or the equation associated to 99 is lesser. Okay, moving ahead. Yep. Now we'll have to check this one. 6 plus 4 is 10. 10 plus 2 root 24. Similarly, 8 plus 3 is 11. 11 minus 2 root 24. Naturally, um, this is nothing but 12, a little much more than 12. And this is definitely somewhere very close to 9 or even less than 9. So, simple squaring helps you out a lot. Now, this is a decent question. It says the square root of this number is what? It talks about 1 by 4, 1 by 9, 1 by 25, 1 by 49, and it is divided by 36 by 121. I'll do the reciprocal to bring it to the point 121 by 36. I am trying to bring all of them back to the normal side. Okay. Now quickly taking them through the square root. The square root of 121 is 11. Whole upon the square root is 2, then 3, then 5, then 7 and 6. 5 2s are 10, 3 7s are 21, 21 6 are 126. So 1260. This is 11 upon 1260 is my answer. Okay, 11 upon 1260. It was pretty much doable. That's why I did it in a jiffy. Okay, moving ahead. Now, the cornerstone of all simplification questions, which is called componendo and dividendo. Okay, componendo and dividendo. So, what happens in componendo and dividendo is that there are two separate ratios. If I have to apply a componendo, what I would do is in the numerator, I would have a plus b, and again in the numerator on the right hand side, I would have a plus c plus d. This this operation is called componendo. Now, if I wish to apply dividendo, I would have a upon a minus b upon c minus d. And I wish to apply a combination of componendo and dividendo. What I would get would be a plus b upon a minus b is equal to c plus d upon c minus d. Okay, so this is how componendo and dividendo works, and this is very very useful because in such a question you might take a lot of time to solve it, but it can be solved very quickly. I'll tell you the quick method. 2a is common, 3b is common, so we can apply componendo and dividendo because it is applied on uniform questions. Okay, so the answer would be 2a upon 3b. Now on the right hand side the same thing will be applied, componendo and dividendo. 18 plus 7 is 25 and 18 minus 7 is 11. So I need to find out the value of a and b. They cannot be found out separately, only a ratio can be figured out. So a upon b would be equal to 75 upon 22. Okay, we cannot find out the value of a and b separately. We will always get them in pairs of a and b only. Okay, because there is only one equation and there are two variables. In such a case, you can only establish a relationship between the two variables. You cannot find out absolute values of them. I hope we are good. Moving on to the next question, and this is the last question of the day. See this. There is a plus sign, there is a minus sign, and the same equation here. This 2, I'm assuming there is a 2 upon 1. This doesn't harm my question at all. Root 3 plus x whole upon root 3 minus x. Componendo dividendo applied. 2 plus 1 is 3 and 2 minus 1 is 1. Got it? Let me square both sides quickly. So 3 plus x upon 3 minus x is equal to 9. Again, assuming there is a 1 in the denominator. Again, applying componendo and dividendo. 3 by x, 9 plus 1 is 10. 9 minus 10, sorry, 9 minus 1 is 8. Okay. So the value of x needs to be found out. 8 3s are 24. 24 by 10. The value of x is nothing but 2.4. And that is where we end our chapter, simplification. Thanks for being here, and do ask all your doubts in the comment section. I will reply to each one of them. Okay. If you have any problem, if you want me to reintroduce a concept, if you want me to reteach anything, I would be more than happy to do it.